Okay, hello everyone. Welcome to our 1 year celebration and update about the Wolfram Physics project. So what I want to do here, I'll talk for a bit about kind of how things have been going with our project. I think Jonathan Gorab will then make a few remarks, and then we'll turn this over to Q&A, and we're happy to go on as long as people are interested in asking questions. We'll keep trying to answer them. So a year ago today, at this time, we did our first live stream launching Wolfram Physics project and a project to find the fundamental theory of physics. So you might ask, a year later, how is it going? The answer is, it's going really great. It's going spectacularly. It's going better than I imagined it could possibly go. And I think there's a lot of good news. I think the most fundamental piece of good news is it really does look like us humans are actually going to be able to understand how our universe works. And the understanding we're getting is something very beautiful. It's kind of an end point of an attempt to sort of formalize the way of thinking about things, and we're able to apply it to our universe. That's one thing. The other thing is that a lot of work other people have done, particularly in areas of mathematics and mathematical physics, that one might have thought, the new paradigm comes in and pushes everything else aside. That's not what's happening. What's happening is that we are providing kind of a low-level machine code to describe how the universe seems to work. And all these various approaches in mathematical physics seem to dovetail beautifully. It seems like what we're providing is a foundation, and they're describing what happens at higher levels. And we're both able to use what those approaches bring to us, and we're able, I think, to suggest new directions and new initiatives for those approaches. So it's really a wonderful thing. I mean, I think that in a sense, when we started this, I started this kind of direction probably 30 years ago, trying to figure out what might be underneath the physics that we know exists today. What kind of could we understand from what we had seen in the computational universe of simple programs? Could we understand whether the things we discovered there were applicable to our whole physical universe? And the answer is they absolutely are applicable, and we're seeing how that works. And in a sense, I think one of the where we are at, it's like trying to find the fundamental theory of physics is like trying to sort of climb what might be thought of as essentially the single tallest mountain in science. I think the main thing we can definitively say is we're climbing the right mountain. We've still got a ways to go to get sort of all the way to the top, so to speak, but already from where we are, the view is terrific. And we're just able to understand an awful lot of things. So in the past year, we've both made a lot of technical progress on the project, understood a lot of things. We've also, something very surprising that's happened is that it's turned out that the formalism we've built is applicable not just to physics, but to lots of other things as well. It's also turning out that the formalism we've built and the models we have are able to deliver kind of near-term practical applications in physics. One of the things we're excited to see is when we start being able to make experimental predictions that people can go out and look at, where there's a real surprise that comes from our models that wasn't something that anybody had ever expected before. We have a number of those things where there's more development that has to be done to get those to the point where we can actually say, turn this telescope in this direction and look at this, or look at do this particle physics experiment and look at this. We're not quite at that point yet, but we are at the point of knowing what is the sort of checklist of possible absolutely bizarre phenomena that our models suggest that really haven't been things that people have imagined to consider before. But I think for me, one of the things that's been most interesting in this past year is almost the understanding the philosophy of the project that we're doing. In a sense, what we're doing is we're trying to find a fundamental theory of physics. We're trying to find a formal description of the world that can give us everything we see in the actual world. We're trying to, in a sense, turn physics into mathematics. And I've sort of been understanding more about kind of the architecture of that process, what it really means to do that, and how we as humans, as sort of observers of the universe, fit into that story, and kind of how the fundamental things we've discovered about the computational universe fit in with what we're discovering about the physical universe. And I would say, sort of to summarize what I've learned, I think there are sort of three big pieces to the picture. So in a sense, what we now imagine is that underneath our whole universe is some simple, essentially computational rule, which when run enough times, and maybe it's running, a rough estimate might be 10 to the 450 rule applications per second in the universe as the universe is today. So lots of computation that's happening. That computation is doing something. The question is, what is that computation adding up to? What is that computation achieving? What that computation is achieving is something that is computationally irreducible. That is, it goes through all those steps of computation, and most of those steps of computation, you couldn't know the answer to those steps without effectively having to follow each of those steps. So in a sense, the process of the evolution of the universe isn't a waste of time, so to speak. It's not the case that we can just say the end of the universe is this. We know immediately that. With the detailed evolution of the universe is something computationally irreducible. There's something where the individual pieces of what's going on are things that can't be worked out except by explicitly doing those computations. Now, another thing that is an important piece of this picture is time, which is something that's always been somewhat mysterious in science, and there are different kinds of time, whether it's psychological time or thermodynamic time, cosmological time. Time in our models is something very definite. It's this inexorable process of the application of underlying rules leading to this computationally irreducible thing being built up, and that thing is the history of our universe. So in a sense, time is something that is the progress of computation in the universe, is the passage of time in the universe. So sort of the first big feature of how to think about the universe is this phenomenon of computational irreducibility, that from this underlying rule, there comes that this computation is being done that is an irreducible computation. So I had thought before we really got seriously started with this project a year and a half ago, that it would be the case that we would get so enmeshed in computational irreducibility that we'd be very lucky to be able to say anything about even what happened after 10 to the minus 1,000 seconds in the very beginning of the universe. That computational irreducibility would bite us in not allowing us to make further progress beyond just saying, well, here's a rule, and we can follow it for a few steps. And will it produce what the universe actually shows us today? We don't know, because we're stuck just following this rule through this process of irreducible computation. That was what I thought was going to happen. The really spectacular thing is that didn't happen. And the reason it didn't happen is because I think it's sort of a big story of science. It's kind of a struggle between computational irreducibility and computational reducibility. Computational reducibility happens when you can say, well, this system is doing all its computation underneath, but in a sense, it's wasting its time, because I can just say, I can come in and say, I've got this other sort of better computation where I can just say the answer is going to be this. That's computational reducibility. And that's the thing that, in a sense, people got very used to in the tradition of mathematical science and so on that's existed for the last 300 years, that you could just plug a number into a formula and see what the answer is. It wasn't an irreducible computation that had to be done. But what we discovered is something kind of remarkable. In a sense, we knew a piece of this already. We'd known that within any system that shows computational irreducibility, there will always be actually an infinite number of pockets of computational reducibility. Those are sort of slices of the behavior of the system that can be understood. The ultimate precise behavior of the system is irreducible. It's something where you just have to follow each step to see what happens. But there are slices, particular features of that evolution that can be understood. Well, it turns out that the slices of what goes on in our universe, the computational irreducibility of our universe, the slices that can be understood, we can kind of enumerate the ones that we found. And it turns out one of them is general relativity, one of them is quantum mechanics, and another one, slightly more junior one in some ways, is statistical mechanics. So what's remarkable is the slices of computational reducibility that we found in this sort of computationally irreducible universe are precisely the theories that are the pillars of physics as it has existed today. So in a sense, there's this computational irreducibility underneath. That is the thing that is generated by these computational processes that sort of underlie the machine code of the universe. But then we found certain slices of computational reducibility, and those slices are precisely the pillars of physics as we know it today. So if we zoom out a little bit and think about sort of how that comes to be, here's the more general picture. The more general picture is, in order to understand the universe, well, it could be the case that everything that happens in the universe is just computational irreducibility, that there's nothing predictable about anything that happens in the universe. It would be hard for us to do what we do if it was the case that everything in the universe was fundamentally unpredictable to us. But so the question is, if we were sort of existing in the universe as observers of the universe, how could we tell anything about what's going on? If everything is computational irreducibility, we would have to essentially have infinite computational abilities to be able to piece together anything that's going on. But let's just say that we have bounded computational abilities. Then it turns out that all we can sample in the universe are these slices of computational reducibility. And with the computational bounds that we have, it's turned out that we get these particular slices of computational reducibility, which correspond to the theories we know in physics. So sort of that's the logical structure, in a sense, of our models, is there's this kind of underlying rule. It is a very simple thing, but when it's run as often as the universe runs it, it produces this irreducible computation. But yet there are features of that irreducible computation. There are these slices of computational reducibility, which we as computationally bounded observers, that is how we experience this whole giant computationally irreducible evolution of the universe. And the slices of computational reducibility that we find are precisely, it turns out, the big theories of physics. So that's kind of the overall architecture of what we're seeing, is we as computationally bounded observers have to sample slices of computational reducibility. The ones that we sample turn out to be the theories of physics that we know. And so in a sense, what we've done here is we've found a machine code that underlies those existing theories of physics. From that machine code, you can kind of build up and look at the limit of very large numbers of these tiny computational components and see, yes, that reproduces these existing laws of physics. But in order to say that, we have to be dealing with computationally bounded observers. If it wasn't for the fact that we're computationally bounded observers, we would not observe the laws of physics that we actually observe today. It doesn't require a lot of detail about us as observers. It requires just knowing that we are computationally bounded observers, and that then implies the presence, the existence of things like general relativity and quantum mechanics and so on. So it's kind of, to me, it's a very elegant kind of explanation of how the universe comes to be the way it is. Now, if you say that there are other things you can go further and talk about, you can talk about questions like, why did we get this universe and not another? And we're actually able to make a serious answer to that question. The answer is that in some sense, there's a sort of super version of relativity. Relativity tells us that the reference frames in terms of motion that we're in don't affect how we perceive the laws of physics. But there's and as I'll talk about, there's kind of a second level of that kind of relativity, which is what leads to objectivity in quantum mechanics, the existence of an objective reality in quantum mechanics. That's a kind of quantum reference frame. We'll talk about that later. But there's a third level, which we call rulal reference frames. Reference frames, well, so I should explain. The thing you might say is, well, you're trying to find the rule for the universe. Well, it turns out that you can ask the question, does the universe run a particular rule? Maybe the universe runs all possible rules. We're going to talk about the fact that even when you have a particular underlying rule, that rule is run in all possible ways, and that's what essentially leads to quantum mechanics. But you can go beyond that and say, you can just say, run all possible rules. Now, you might say, how would the universe have any coherence? What would you be able to say if you were just saying, we're running all possible rules? The reason you can say something is because when you run all possible rules and you have time progressing, these possible rules lead to sort of different branches of history, but those branches of history are deeply entangled. Because, for example, two different rules could lead to different outcomes. then they could lead to outcomes that merge and so on. So even though you're dealing with all possible rules, there is a rich structure of sort of the entanglement of the possible histories of the universe. And you can ask in that sort of rich structure that's produced, that is sort of a computationally irreducible thing to produce all of that, you can say, how does a computationally bounded observer perceive that? How does a computationally bounded observer embedded within that elaborately branching kind of thing, how does a computationally bounded observer perceive it? Well, they pick out slices of computational reducibility. They're actually reference frames, not with respect to motion, not with respect to quantum reference frames, quantum measurements. They are reference frames with respect to kind of the description rules that you're using, the description language that you're using to describe the universe. So in a sense, what's happening is there is with a particular observer of this universe generated by the running of all possible rules, you are taking a particular slice based on a particular observer's choice of how to describe what's going on. And that particular slice will then, if the observer is computationally bounded, that particular slice will inevitably show certain laws of physics. And those laws of physics are the ones we observe. And but the point is that you don't have to commit yourself to what is you're saying you can run all possible underlying rules. You're merely taking some particular reference frame to perceive what's going on. And in that reference frame, if you are computationally bounded, you will observe the laws that we actually observe in physics. So in a sense, it's a very bizarre answer to the question of why this universe and not another one. It's that all possible universes, in a sense, are in there. It is that we are picking a particular reference frame. And by the way, whatever reference frame we pick within certain constraints and this computationally boundedness of observers, we will then deduce these same laws of physics that we have found to be true. Now, it also means that there are all kinds of exotic things one could start thinking about alternative rulal reference frames and totally different descriptions of the universe and so on. Maybe I'll talk a little bit about that later. But let's go. So that's kind of the overall kind of philosophical architecture of what we're dealing with. And it is something where the sort of, to me, the elegance of what's revealed about how the universe works and is put together is really truly remarkable. And the way that it sort of gets its fingers into these different areas of mathematics and mathematical physics, kind of sampling some of the upper reaches of kind of what's been achieved in terms of the creation of abstraction in mathematics and so on, are being sampled and getting a kind of concrete foundation in the way that we're setting up our models of physics. And that to me is something very exciting. So in a sense, let's come a little bit more down to earth and talk a little bit more about what's actually been happening with what we figured out about how the universe works and how our project describes it and so on. And then I'll talk a bit about some of the ways that we've been able to apply the project to actually doing computations in physics that are useful here and now. Then I'll talk a bit about how we can apply the formalism that we've developed even outside of physics. I'll also talk a little bit about some of the experimental implications of our models. Okay, so let's start off with kind of what's the universe made of, so to speak, according to our models. Well, one of the foundational ideas of our models is the thing that people have sort of believed about space for the last couple of thousand years isn't true. That space is just this background, this manifold in which you put points down and you say, I can be at this position or that position or another position. Instead, space is actually made of stuff. Space is made of what one can think of as atoms of space, as discrete elements, points. And by the way, I should make it clear that this idea is something that 100 years ago people would not have found surprising. It's just people hadn't managed to make the idea of space as a thing with discrete elements really work. I mean, even a couple of thousand years ago, people were thinking about these same ideas. What's remarkable and what's happened as a result of kind of the computation-informed stack that we've been able to build is that those ideas actually work and actually give one a way to understand what's going on. So sort of the underlying picture is space consists of a large number of discrete elements, maybe 10 to the 400 of them in today's universe. Those are the sort of the atoms of space, the discrete points that exist in space. The only thing that we say about those atoms of space is how they're related to each other. We might say there is a relation that connects these 4 atoms of space, and there are zillions of these relations. And as we think about all these different relations, we can think about them building up a hypergraph. You can think if all the relations were just pairs, we would just say this node in the universe is friends with this other node in the universe, and we build up this giant sort of friend network of elements in the universe. But so the foundational idea of our models is what's in the universe is just atoms of space. That's all the universe is made of. And those atoms of space are related, connected to form this giant hypergraph. And everything that exists in our universe is just features of that hypergraph. All the space that we know about, the space that we know about is fundamentally made of that hypergraph. And everything, all the particles, the electrons, everything that we see happening in the universe, it's all features of that hypergraph. And in a sense, it's worth remembering the analogy. People didn't know that fluids like water were made of discrete things 150 years ago or something. It then became clear that water, even though it behaves continuously as a fluid on large scales to us, underneath it's made of discrete molecules bouncing around. And so it is now, we think, with space, that it's made from these discrete atoms of space, but it's not something as direct as just they're bouncing around. There's this abstract network, this abstract collection of relations that define this hypergraph that represents space. So the things that we've known, we knew a year ago, I knew this even in the 1990s, that you could make from this kind of network, you could make something where the large scale limit of this network, just like the large scale limit of a bunch of molecules bouncing around is the continuous fluid of water or something. So similarly, the large scale limit of these atoms of space connected in these ways would be like space as we perceive it. So that's kind of the first piece of this picture, is that we have kind of this giant hypergraph that represents the spatial hypergraph that represents space and everything in space. So then the second piece of this is time, the actual evolution of this hypergraph. We have some rule that just says, whenever you have a little tiny piece of hypergraph that looks like this, transform it to be one that looks like this. And that sequence of transformations changes the structure of space and the structure of everything in space, and it continually does so. And that is the progress of time. That progressive rewriting of this hypergraph is the progress of time. One of the things that's sort of interesting, I suppose, about the philosophy of what's going on is, in our model, there is nothing permanent in the universe. The universe consists of something that is being remade and reformed at every progressive moment. So there is no, space doesn't hang together except by virtue of the fact that there is activity in space kind of knitting it together. There's nothing permanent. Everything is created by the dynamic sort of process of computation that goes on in the universe. Everything, including the knitting together of space. So that's kind of the first part of the model. And one of the things that we had known a year ago, I'd even known in the 1990s, is that the large scale limit of the application of these individual rules to a spatial hypergraph like this gives you general relativity. It gives you Einstein's equations. And we can, one of the features of this hypergraph that represents space is we don't even know how many dimensions it has. And I will say we don't yet know why the universe is 3 dimensions of space. We know why it's 1 dimension of time, that we understand now. We don't know why it has 3 dimensions of space on average on a large scale in the current universe. That's something that 3 is a dynamical variable in our models. It's something which, depending on the details of how this connections between these different atoms of space work, that you can get any number of dimensions as the effective dimension of the universe. And so that's the way that works. Now something that's kind of interesting about the universe in our models is the universe probably started infinite dimensional. People wonder about how the different parts of the universe would get sufficiently connected in the very early universe. The answer is, I think, the universe was effectively infinite dimensional. And as the universe evolved, it kind of, the dimensionality of the universe cooled down to the point where now it's roughly 3. And I say roughly 3 because we suspect that there will be dimension fluctuations in the universe. We suspect that from the early universe, there may very well be kind of a signature of those dimension fluctuations that may be visible in the structure of the cosmic microwave background. There may even be pieces of the current universe that have dimension fluctuations, dimension 3.001 or something instead of 3. And that's one of the experimental directions that we're interested in, is being able to detect the propagation of photons through varying dimension fluctuations in the universe. But that's one of the things that in our models, probably the universe started infinite dimensional. It started as a network that was very, very, very connected and progressively became something that is on a large scale like a three-dimensional manifold. But one of the things that comes out of our models is a kind of a mathematical proof that, subject to certain conditions, which are essentially the presence of computational irreducibility and the computational boundedness of observers, which is more mathematically stated as the computational boundedness of the description of reference frames, or the gauges that you specify to describe the structure of space-time. With those constraints, you can derive the Einstein equations for general relativity. You can derive the fact that the universe that the curvature of space will correspond in the way that the Einstein equations say. Now, one piece of the Einstein equations that I didn't really describe here is the Einstein equations relate the curvature of space to the presence of energy momentum in space. Now, in our models, and this is again something that I didn't really expect would work out as nicely as it has, the energy momentum, I thought we were going to have to understand what particles and electrons and all those kinds of things are in our models before we'd understand energy momentum. But it turns out that there's a bulk understanding of energy momentum, and that we knew about in our models more than a year ago, that allows us to set up the Einstein equations. So in other words, we don't have to say the energy momentum is made of a bunch of particles. We can just say in the bulk, the energy momentum corresponds to a feature of the spatial hypograph and its evolution. And actually, it's really simple. The energy is essentially the amount of activity in the spatial hypograph. And momentum, it's a little more complicated. It's because you have to define what you mean by space and time and so on. And there's a whole relativistic story. But essentially, energy is the amount of activity in the spatial hypograph, the amount of rewriting that's happening in the spatial hypograph. Mass is kind of the amount of kind of permanence to that rewriting. The extent to which there is any permanence in the universe is a feature of mass. And energy is the extent to which there's just pure activity in the universe of any kind. So, and from that we can, and we talked about this a year ago, we can do all those nice crowd-pleasing things like actually derive E equals mc squared, not say it's a feature of the model based from its mathematics, but actually derive it from the underlying machine code of the model. So okay, so then we can derive Einstein's equations that relate the curvature of space to the presence of energy momentum. And Einstein's equations also tell us that if we have a straight line, if we say we think a particle that isn't acted on by any forces will just go in a straight line, or a geodesic, a shortest path, and that's quote straight line depends on the curvature of space. So if it was flat space, the straight line will be truly flat. If it wasn't flat space because of the presence of energy momentum, the line will be curved. And that in standard general relativity is the source of the force of gravity, that you're producing curvature in space by the presence of energy momentum. Then the geodesics are deflected, and that represents the effective force of gravity on a test particle. Okay, so in our models, we can derive all of that stuff, and we can then start asking about all the different phenomena in general relativity. All the things like event horizons and black holes and all those kinds of things. And sure enough, those things can happen in our models. And it becomes very clear how things like event horizons work. I should have explained one of the things about our models, and the thing that actually leads originally even to special relativity is the following point, that in our models, which involve these hypergraphs and all this rewriting and so on and so on and so on, we think about how does an observer perceive what's going on? One of the key facts is that the observer is part of the universe, sort of by definition. And so the question then, how does an observer that consists of all these rewriting events and all this kind of thing, how does an observer whose mind, whose brain is based on all these rewriting events perceive all these rewriting events that are happening in the universe. And it turns out that the way to understand that is through these things we call causal graphs. The observer, what they are capable of telling is what the causal relationships between different updating events in the universe are. And so we developed this kind of causal graph that represents that network of causal relationships. And it's because of the structure of that causal graph and a phenomenon we call causal invariance, which is a property of rules, which actually we think now can also be an emergent property of rules. Because of those things, it turns out that the observer, independent of kind of what reference frame, okay, so an observer, okay, to begin with, if we look at what's happening in the spatial hypergraph, we have all these different atoms of space and they're all getting updated and it's all a very confusing thing. But an observer wants to make sense of this. An observer wants to come in and say, I know what's going on. There's this particular moment in time, and at that moment in time, space has this structure, and at the next moment in time, space will have another structure, and so on. And defining what we mean by this moment in time, because after all, there are all these different updates that are happening, and they're all happening independently. To define what we mean by this moment in time, we have to define a reference frame of the kind one thinks about in relativity. And there's a constraint on what kind of reference frame we can define because we are computationally bounded. We can't define a reference frame that's too complicated and squiggly. We have to define a reference frame that has a certain simplicity. And it's the simplicity of that reference frame that leads in the end to relativity, to the validity of relativity in our models. So it's sort of a combination of there's a certain degree of randomness that comes from the computational irreducibility underneath, together with our computational boundedness leading to a certain choice of reference frames, and that ends up leading to together with causal invariance, leads to the validity of relativity and leads to all these different phenomena. But so this causal graph, the characteristics of things like black holes with event horizons, they are visible in this causal graph because an event horizon is something where, for example, in the case of a black hole event horizon, sort of events that happen within the horizon can't affect things outside the horizon. And you explicitly see that in our causal graphs. And in fact, you can also get in the universe much more exotic things than standard black holes and so on, because in our models, there are all kinds of other kinds of structures like higher dimensional lumps, space tunnels that exist in higher dimensional space within the universe and so on. The other big feature is that in traditional general relativity, it's very hard to understand, for example, how you can't, the structure, it's like you have a rubber sheet, the universe is made of a rubber sheet, a common model, but you don't get to like take scissors to the rubber sheet and cut a piece out. You don't, and sort of have the thing dynamically separate. The scissors are not described by the model. And you can, so in our models, the actual structure, the topology of space can dynamically change. And so, for example, pieces of the universe can simply disconnect. And the notion of sort of what happens at the singularity at the center of a black hole, we actually have a way of precisely seeing that. We don't just have to say, oh, sorry, our equations don't apply. We get to explicitly see the breakdown of the structure of space-time at those singularities. So one of the things that we've done, this is a piece of work by Jonathan Gorard, is to actually use our models explicitly as a way to do numerical general relativity. So normally when you try and study the merger of two black holes, to generate gravitational waves and all those kinds of things, the way you do it is you say, we've got these partial differential equations, which are Einstein's equations. They're kind of hard to work with, but we've got these equations. Now we're just going to solve them and we end up having to solve them on a computer. We can do some algebra, but then we'll end up having to do numerical computations. We're going to end up taking these nice continuous equations that describe this sort of continuum structure of space-time, and we'll have to break them down into some kind of discretized pieces that can actually be fed to a computer and on which we can do numerical computation. So that's the traditional way to do things. You go from the Einstein equations, which are continuous equations, you kind of shatter them to something discrete where you can do explicit numerical computations. And then you hope that your numerical computations correctly represented what happened to these continuum equations. Okay, so we have an alternative approach. In a sense, it follows in spirit what I did a long time ago with fluid dynamics, of kind of working up from cellular automata that could describe fluid mechanics rather than working down from the fluid equations and discretizing them. So what Jonathan has done is to take the equations, take our models, take our hypergraph rewriting models, and just say, use that as an actual model for space-time and do computations in somewhat large examples of that. And it turns out phenomena like black hole mergers, you can actually see those, you can actually compute those in these models. So instead of going from the Einstein equations down, you're going from our underlying models up. Now, in truth, to get to our real universe, we have to go 100 orders of magnitude up from our models. But Jonathan doesn't have that big a computer. The universe wouldn't provide it either. So we're just going a small distance up, but it turns out that's sufficient to be able to see the phenomena and be able to quantitatively compute things about black holes. And so this provides a practical method for doing numerical relativity that looks very promising. And it's in a sense, what it's doing is it's making use of, well, it's making use of many things. It's making use of the fact that sort of the adaptation in numerical analysis is happening by the virtue of the actual dynamics. There's nothing which has to be done from outside. It's making use of the fact that the dimensions of space, when you discretize, you're usually making a discrete mesh in a fixed number of dimensions. We're not doing that, and that turns out to be a more powerful thing to do. But more than that, it allows you to really see what's happening in the formation of black holes. And for example, when you have black holes that are spinning very rapidly with J greater than M, for example, supercritical black holes, you can actually see explicitly what happens when you, for example, combine two black holes and they produce a black hole that is supercritical. What happens is very bizarre. Basically, a piece of the universe breaks off. And as it's breaking off, you see these kind of causal edges that are just, a piece of the universe is kind of hanging by a thread, quite literally. And it's quite possible that it'll actually be possible to observe some kinds of discreteness in the gravitational waves that are produced by that process as a way to explicitly see kind of a gravitational microscope to kind of be able to see the underlying structure of space-time that we were not able to see in any other way. Now, it's always a challenging thing when you have a numerical scheme like this, and we're only going a small number of orders of magnitude up rather than the 100 orders of magnitude that we might need for the real universe. The question is, how accurate is what we're seeing there? How much can we trust sort of the places where we're seeing through to the underlying kind of discreteness of physics? Sort of there's an analogy in fluid dynamics. In ordinary fluid dynamics, you don't know that the fluid is made of individual molecules. But if you go to hypersonic flow at, let's say, Mach 20 or something, then it really matters that there's some, or even Mach 5, it really matters that the fluid, the air, or whatever it is made of discrete molecules with particular detailed chemical properties and so on. And so similarly for us, we have to find kind of what's the analog of hypersonic flow for gravitation. And it seems to be rapidly spinning black holes, although there may be other cases. And in those cases, we can kind of see through to the underlying discrete structure of space. And that's what we'll see in our models. Now, one very important thing that we've kind of understood about our models is a certain genericity to them. So I talked about how sort of there's this underlying computational irreducibility, and we're seeing certain slices of reducibility. I also talked about how sort of all possible rules can be run. That's an important point, because what's happening is at the level of these computationally reducible slices, it actually doesn't matter within certain constraints what the underlying rules are. Now, is that surprising? Well, let me give you an analogy which might make that less surprising. The analogy is thermodynamics. We have certain rules of fluid mechanics. We have certain rules like the second law of thermodynamics, and they apply to air, to water, to any kind of material. It doesn't matter what the details of the molecules are. On a large scale, you still get the same aggregate behavior. And so it's the same thing that's happening in the case of the structure of space and so on, that these underlying rules, there will be some things for which they're important. When you see through, when you have your gravitational microscope and you can kind of see down into this sort of discrete layer, then it matters. But when you're looking at the large scale limit of the continuum limit, it doesn't matter. For the same reason that it doesn't, but the same way that it doesn't matter to the equations of fluid dynamics what the underlying structure of the molecules is. Now, by the way, this is a more integrated story than I'm giving it credit for, because statistical mechanics, the theory that tells one that, for example, that talks about things like the second law of thermodynamics, that it turns out that the underlying structure of the second law of thermodynamics, the cause of the second law of thermodynamics is the same underlying computational cause as the cause of the validity of relativity, for example. How does that work? Well, in statistical mechanics, we have the idea that we've got a gas, we've got a bunch of molecules bouncing around in a box. The big idea of the second law of thermodynamics is even if you start those molecules off in what seems to you like a very ordered state, after a while they'll bounce around a lot, and as far as you can tell, they'll seem to be in a quite disordered state. And you can measure that by looking at entropy, which is basically the number of possible configurations consistent with the measurements you make about the state of the gas, those kinds of things. It will seem like the gas is going from this ordered state to this very disordered state. Now, in truth, if you were a very computationally sophisticated observer of the gas, you would say, no, that's not at all what's going on. The gas starts from some initial configuration. It just follows the equations of motion for the molecules, and it ends up in some other configuration. It's just, why are you saying that there's anything different between the initial configuration and the final configuration? The final configuration is just what you get by following the laws of motion. Well, the reason we say there's something different is because we are computationally bounded observers of this gas. In other words, we don't get to trace every single gas molecule and work out its equations of motion all over the place. We just look at the sort of coarse-grained, large-scale structure of the gas. For example, we measure pressure and temperature and things like this. Those are large-scale features not dependent on individual molecules. And so in a sense, we are computationally bounded observers of this statistical mechanical system, this collection of molecules, and it's that computational boundedness that leads us to conclude that things became more disordered, or put more formally, that entropy increases. So it's actually been quite mysterious how the second law of thermodynamics really works at a foundational level. It's something I figured out in the 1990s, actually, that it's all a story of computational irreducibility, that the underlying dynamics is computationally irreducible. The part that I understand much better now is thinking about us as computationally bounded observers of the gas, and the fact that we can only be sensitive to certain features of what's happening. And when we look at what the features of those features that we're sensitive to, we can deduce certain overall laws associated with those features. Even though we can't say anything about the detailed individual molecules, we can say something about those overall sort of computationally reducible features, and the overall things we can say are things like the second law of thermodynamics. And so it's the exact same thing that's going on in the case of the structure of space. What we're seeing is there are sort of these underlying atoms of space, and they have certain rules, but it actually doesn't matter in detail what those rules are when we're only looking at the features of space that are captured by general relativity. If we want to go below general relativity, go to sort of hypersonic flow, a gravitational microscope, so to speak, then it's going to matter what those underlying rules are. And again, as I was talking about earlier, there's this complicated issue of rule reference frames and which rules you attribute the evolution of the universe to, but fundamentally you're going to see down to these underlying discrete laws. So in any case, the thing that I think is interesting and what I like very much about Jonathan's work in this area is that we've actually got a case where people say, well, does your model really reproduce general relativity? Well, the answer is, well, we can actually use our model as a practical way to compute things in general relativity. So that gives us a very operational way to know that our model is really, and so insofar as you say, well, does your model have predictions? Well, yes, it has a boatload of predictions. It has basically the predictions of general relativity. We just got those, we got to leverage those for free, so to speak, directly from our model without going through Einstein's equations. We just got those predictions directly from this sort of the underlying structure of the hypergraph and so on. So that's kind of the and by the way, when that's in a sense what I like about that is when it's sort of a proof by compilation for our models. The fact that we can kind of compile the overall kind of a description of, here are two black holes, they're doing this. We compile that description into the low-level machine code that represents our models. Then we can do computations there, and then we can find out, yes, they agree with experiment in the same way that general relativity agrees with experiment. So that's kind of a little bit on what we know now about the structure of space. There are some neat hacks. I was interested a few months ago in what can we say about faster than light travel in our models. And it turns out that it's kind of a bizarre thing that faster than light travel is a story of being able to do the equivalent of beating the second law of thermodynamics. Because what's happening is, in our models, there's a certain light cone, a certain causal cone associated with any given event, what can it affect? The issue is, and that cone kind of expands at a certain rate. The issue is, how does space line up with the way that cone expands? And in a sense, what happens is, if you could, within space, there's all this complicated dynamics because it's made from this hypergraph, and there are little pieces that behave like kind of space tunnels, but they're very tiny space tunnels. But if you could navigate exactly correctly and go from one space tunnel to another, to another, to another, you would be able to kind of hack the structure of space and effectively go faster than the speed of light. But so the statement that you can't go faster than the speed of light is a statement that in the structure of space, as the structure of space is, you can't go faster than the speed of light. But when you go underneath the structure of space as it is, and you start looking at this discrete underlying structure, you get to, if you could kind of predict, if you could do all the computations to know exactly where to go in this kind of network that represents space, you would be able to effectively go faster than light. It's just like if you were sitting on a gas molecule and you're trying to figure out, how do I get to the other side of the room? The generic way the gas molecule is going to move is by a random walk, by diffusion. It's very slow. But if you were able to pick, every time there was a collision, you were able to pick, oh, I'm going to hop to that other gas molecule, and you were able to do the very elaborate computation necessary, you could actually work out, you could actually go at sort of the speed of sound across the room just by hopping from gas molecule to gas molecule. And so it is with the physical universe, that in principle, you could sort of hack the structure of space to be able to do that. Can we do that in practice? Absolutely not. Gazillions of orders of magnitude, 100 orders of magnitude away from being able to do that. Our experience of space and the very fact that we believe that there is a coherent notion of space is a consequence of the fact that we're operating on much larger scales. So that's something where, it's going to be a very long time, if ever, that it's possible to leverage that feature of the hacking of space to do something like that. But it's sort of interesting to see from a kind of conceptual point of view how such things come out in our models. So anyway, so that's a little bit on sort of the structure of space. The thing to remember is everything that we care about in space is a tiny fraction of the actual activity in space. Most of the activity in space has to do with knitting together the structure of space. Maybe 1 part in 10 to the 120 of what's happening in the universe is actually producing and representing all of those particles and all those things that we are familiar with. Now, maybe I should say a little bit more about the structure of space. So a particle has to be some kind of topological obstruction. It's kind of like a vortex in a fluid. It's something, a vortex in a fluid is something that has a certain degree of stability. It can propagate through the fluid as a thing that is sort of topologically stable. Well, that's how we believe particles work in our universe, in this model. And we have not yet sort of figured out in detail how particular particles work. We're beginning to have clear ideas about how to do that. It's one of the next big projects to work on. It's just sort of find the photon, find the electron type thing. We don't know whether we're going to be able to be that specific. We think we're going to be able to sort of find these underlying localized structures, sort of topologically stable localized structures in this evolving hypergraph, and that there will be certain generic features of those structures, and possibly that the kind of symmetries that exist for particles will be reflected in the kind of ways that those structures can emerge. Well, so let me go to the second sort of big pillar of physics as it is, which is quantum mechanics. And let me talk a little bit about how quantum mechanics works in our models and our greater understanding of that's emerged over the past year. So the key fact about quantum mechanics in traditional physics as compared to classical mechanics is in classical mechanics, definite things happen. You drop a pen, it falls under gravity. You throw something, it goes in a certain trajectory. In quantum mechanics, it is not that definite things happen and things go in definite trajectories. Instead, the idea is that in a sense, all possible trajectories are followed, and we merely get to measure certain probabilities of different outcomes based on those different possible trajectories. So in our models, one of the really spectacular things is that quantum mechanics is not something that you have to kind of add in. It's not something where, oh yeah, we have classical mechanics, we hit the 1920s, we have to invent quantum mechanics type thing. It's that quantum mechanics is an unavoidable, inevitable feature of our models. So we talked about before the fact that in the spatial hypergraph, there are all these updates that are happening. And every time you see a little piece of hypergraph that looks like such and such, you update it in this way. Well, the point is that there can be many different places, many different updates that can happen, many different sequences of updates that can happen. Those define many possible paths of history. Each one of those possible sequences of updates corresponds to a different path of history. And in general, given that you are a particular state of the universe, you can have branching where you get two different states of the universe based on following two different paths of history from those, but because two different updates could be done. But the key fact is not only do you get branching, you also get merging. And because two different states of the universe can have updates which cause them to end up being the same state of the universe. And the structure, we get another kind of graph, we call it a multi-way graph, that it represents this sort of branching, merging of the threads of history for the universe. So the key point is that in addition to the spatial hypergraph, every copy, the spatial hypergraph is that when you follow every possible sequence of updatings, you get this multi-way graph. And the multi-way graph represents all possible threads of history in the evolution of the universe. Now, one of the things we've been working on a bit, this is particularly a Max Piskanoff production, is to try to break down this kind of very complicated multi-way graph and spatial hypergraph story into something where we have a local multi-way graph. In a sense, the thing I call multispace is this thing which is a spatial structure, but kind of puffed out by the multi-way character of these possible threads of history. And so normally in our most simple global multi-way graph, every node in the multi-way graph is a complete state of the universe. In a local multi-way graph, it's a more entangled kind of thing, which is actually pretty hard to wrap one's brain around, but it's, I think, a practical way forward for doing a bunch of simulations, probably going to be quite important in simulating quantum field theory and various other kinds of things. But anyway, let's talk about just the multi-way graph. Okay, so there are these different possible threads of history. And the question is, what can we say about these different possible threads of history? And when we observe there's this kind of multi-way graph, multi-way system version of the universe that involves all these possible threads of history. Okay, so here's a critical fact about the universe and our perception of it, which is we're supposed to be part of this universe. And so our brains are part of this whole story of branching and merging, et cetera, et cetera, et cetera. So we have the very bizarre question of how does a branching brain perceive a branching universe? We have this universe and it's going in all these different branches, all these different possible threads of history, but so are we as observers. We're also following lots of different possible threads of history. And we have to ask, how does the branched brain perceive the branched universe? And the answer is, and this is again an idea of Jonathan's to do with kind of an interpretation of quantum mechanics, it's kind of a way of understanding how that branched brain will perceive the branching universe. And the idea, it kind of uses an idea from a quite different field, from the field of theorem proving, automated theorem proving. It uses the idea of so-called completion lemmas. Essentially what's happening is, the reason there's a correspondence here is because this multi-way graph is kind of the same kind of structure as you get when you try and see what are the consequences of applying mathematical axioms to expressions. The structure of the universe is an expression, the state of the universe is an expression, and there's an axiom that says transform this expression in this way, like x plus y could be transformed to y plus x if it appears in the expression. You say, make those transformations in all possible ways, what you get is a multi-way graph, and a theorem in that setup is then a path that says you can get from this expression to this other expression. There exists a path. The proof of the theorem is that path. And so in that setup, one of the things that comes up is this idea of completions, which are a way of essentially accelerating, deducing what theorems are true. And so what we imagine is that a completion is basically to say, when you have two branches, you just are going to assume that the things that came from a common ancestor are somehow equivalent. You're going to equate those. And that will add essentially something like an axiom to your system. You apply those axioms and you will conclude that the system has certain structure. So applied to us as observers of the universe, what we're saying is there's a branching universe. We're branching brains, so to speak. We end up with we end up concluding that we're kind of gluing these pieces together by completions, because as we say, we know there's something definite happening in us. So these branches, we must assume, are all the same in some sense. And so that notion then causes us to add these completions. Now a thing to say. So okay, so how do we observe? We're observing this kind of quantum universe, and we're observing it. We have sort of these branching brains that are observing this branching universe. Now, just as we pick different reference frames to make sense of the structure of space, so we also pick different quantum observation frames to make sense of the structure of the quantum world. And the other key fact is that in this multiway graph, we have this multiway graph, it's got all these threads of history. Each thread of history, as you progress in that thread, corresponds to the sort of progress of time in the evolution of the universe. If we say, let's take this whole multiway graph and let's slice across the multiway graph, and let's say, let's look at all the threads that exist, all the threads of history that exist at a particular time. We can choose our times differently. That corresponds to different reference frames, but we just say, find some slice across this multiway graph. That slice then gives us something where we have this multiway graph, and all these different threads of history are sort of in different positions in this multiway graph. What are they at positions in? They're at positions in what we call branchial space. It's a version of space that is not physical space. It's a space that is a quantum space, a space that represents the space of quantum states. So each one of these branch threads of history corresponds to a different quantum state. And in a sense, by slicing across this multiway graph, we get this whole bundle of different states, quantum states. And then by looking at the structure of the multiway graph, we have essentially a map of the positions of different quantum states. Now, normally we might think, oh, we're just getting these different quantum states. They're not related to each other, but they are related. The multiway graph gives us relations between these things because they have common ancestry in this multiway graph. And that allows us to build what we call a branchial graph, which represents kind of the common ancestry of quantum states in this branchial space that is this slice at a given time through this multiway graph. So branchial space is the fixed time, in a sense, slice through the multiway graph, just as ordinary space is the fixed time slice through the causal graph. And so this branchial space is then a map of possible quantum states. So we can say this quantum state is close to this other quantum state, and we have a whole sort of structure of that. Now, the mathematical structure of branchial space is something very complicated, and it's something that we've been working towards understanding, and we're getting a better understanding of essentially the coordinatization of branchial space. In physical space, we get to give coordinate systems. We can say it's a manifold. We're just going to represent it as three-dimensional Euclidean space, or a three-dimensional space that corresponds to some metric given by the Einstein equations or something. We get to specify coordinates. We get to say what we get to label points and give them numbers and things like that. We don't know how to do that in branchial space. What we need in branchial space, probably a single slice of branchial space is potentially like a Hilbert space, but the whole time evolution is some elaborate kind of Minkowski space generalization of Hilbert space that is not a mathematically understood thing, although it does have a special case maybe that is twistor space. So in any case, the end result there is that we have this branchial space that represents the space of possible quantum states. And we have this multiway graph that is kind of feeding threads of history into different places in this branchial space. And so now we can ask, well, so what happens in branchial space? What is the analog of, for example, motion in branchial space? Well, we can imagine, we can find sort of things that progress through time and move in branchial space through time, those correspond to threads of history in the multiway graph. And so we can ask the question, just like we talked about geodesics that move in physical space as a function of time, we can talk about geodesics in the multiway graph that in a sense move in branchial space as a function of time. And so those geodesics are in a sense, those represent the evolution of quantum amplitudes. So one of the things in the structure of quantum mechanics and the way that people talk about quantum mechanics is they say, well, there are quantum amplitudes. And what is a quantum amplitude? It's a number, a complex number associated with a particular quantum state. And in that complex number, there are actually two things. There's a magnitude and there's a phase in the complex number. And one of the sort of facts about quantum mechanics is the sort of a good formulation of quantum mechanics is the Feynman path integral, which says that really the only thing you should think about changing in a quantum amplitude is the phase. And it says the phase evolves like e to the I s over h bar, where s is the action. Okay, so the what that's saying is that, so what we think is that the packaging of magnitude and phase into the single complex number for a quantum amplitude is a mistake. That the magnitude of the complex number comes from a different place than its phase. By the way, this is similar to the mistake we think was made with space and time, that packaging the two things together into this thing called space-time, where you just talk about x squared minus c squared t squared as you know, this single quadratic form type thing, that's a mistake, that really space and time are very different kinds of things. Time is associated with this inexorable computational process. Space is associated with all these connections in the spatial hypograph, and it's only an emergent feature associated with the causal graph that causes space and time to be sufficiently the same kind of thing that you can write down the equations of relativity and so on. And we think the same kind of mistake was made in quantum mechanics in packaging together magnitude and phase of quantum amplitudes. So in our models, the magnitude of a quantum amplitude is a result of essentially counting so a quantum amplitude is associated with a particular quantum state, a particular point, and a particular branchial slice through the multiway graph. And what we're saying is that that quantum amplitude, the magnitude is just telling us how many paths get to that particular point. Starting from our initial conditions, how many paths will reach that point in branchial space at that particular time? That's the magnitude. What's the phase? The phase is the position in branchial space. Now that's a squiggly thing, the position in branchial space, because it's not a Euclidean space. It's not something where we can easily assign coordinates. So it's a big challenge to assign those coordinates and say the positions. But if we say how far apart are 2 points in branchial space, that distance apart will be a phase difference between those quantum amplitudes. But we don't know completely how to coordinate our branchial space. But what this is telling us is that as we go down in the multiway graph, and as we deflect the position of a particular thread of history, that deflection is moving the quantum phase associated with that particular thread of history. So what does that mean? That means that what's happening is as quantum evolution is happening, one is deflecting these geodesics, these paths in the multiway graph. Okay, so there's a very beautiful analogy here. In physical space, the deflection of geodesics is associated with the results of gravity and is associated with the presence of energy momentum. So now what about the case of the multiway graph? Well, it's the exact same thing. You can assign an energy momentum. It's also associated with the activity that exists in this multiway graph, characterized by the multiway causal graph, actually. And you can assign sort of an energy momentum there. And then you can say, let's look at how the effect of that energy momentum on a trajectory, on a path, on a geodesic through this multiway graph. Well, just as the presence of energy momentum deflects a path in physical space in the causal graph, so too it deflects a path in this multiway graph. And that deflection, it means that you're being routed to a different place in branchial space. What does it mean to be routed to a different place in branchial space? It means you're changing the phase of the quantum amplitude as a result of the presence of energy momentum. And so let's go back to the Feynman path integral. Well, the Feynman path integral says that it says that energy momentum characterized by the action, which is a sort of relativistically invariant version of energy momentum, that is the presence of action, essentially energy momentum, is causing a deflection, is causing from that e to the I, whatever, that's essentially changing the angle of the phase of the quantum phase. So in a sense, what's happening is the presence of energy momentum in this branchial space is causing a deflection of geodesics in branchial space. Or in other words, the same exact dynamics that happens with Einstein's equations in physical space is happening in branchial space, except the interpretation in branchial space is not, oh, it's the force of gravity, it's, oh, it's the action of quantum mechanics. And so what that means is that the Feynman path integral in quantum mechanics is the same mathematical construct as the Einstein equations in physical space. So which is sort of a remarkable thing, that these two great theories, quantum mechanics and general relativity, are in a sense the same theory. In fact, in the end, what we'll see is that when we come to think about observers, in quantum observers, we have exactly the same story as in statistical mechanics and in general relativity, that the story is the observer is computationally bounded. Therefore, the observer performs certain coordinatizations, and those force one to have an effective description of what's going on that corresponds to a computationally reducible story that corresponds to statistical mechanics, general relativity, and quantum mechanics. So in a sense, quantum mechanics is the story in branchial space of the consequences of a computationally bounded observer observing computationally irreducible processes underneath. So there are many details to fill in. I mean, you can ask about all kinds of things about the uncertainty principle, and that's related to sort of the curvature in branchial space analogous to curvature in physical space that leads to sort of the non-closing of sort of rectangles and parallel transport in physical space. That analogy is the uncertainty principle in quantum mechanics and so on. And you can go on and start seeing all these different features of quantum mechanics. Okay, so one of the things that you can start asking, how do you reproduce sort of standard quantum mechanical things? One thing we did was look at the double slit experiment. It's a sort of an adventure of how do you map the spatial representation of where does the photon go onto the branchial representation of quantum phases. And it's a rather elaborate thing, and perhaps a little rickety, but it seems like one can get sort of a coordination of branchial space in that case, and we're now understanding in a much deeper way how the coordination of branchial space works, but you sure enough get the right kind of behavior for this double slit experiment that you would expect from standard quantum mechanics. But the surprising thing, again, is that we're able to talk about quantum mechanics without talking about it particles. We're able to talk about, in a sense, bulk quantum mechanics, and we're able to go a long way in talking about that. So one of the big things that's happened this year is understanding the correspondence between our models and the categorical approach to quantum mechanics, the approach to quantum mechanics based on category theory. And in a sense, this is taking us into a mathematically sophisticated direction. I should say, by the way, that one of the things that's happened in the general relativity case is understanding the connection of our models to causal set theory, which is an existing mathematical physics approach. In causal set theory, and we're now talking about space-time for a moment, in causal set theory, the idea is you just sort of throw down these different events in space-time, and then you say all you can talk about is the causal graph that corresponds to the connections between these events. And it's been difficult to understand in causal set theory how you get things like Lorentz invariance, because that depends on having a particular way of kind of throwing down the points in space-time to correspond to these events. Well, it turns out, and there's another piece of work by Jonathan, that what our models do is to provide an algorithmic generator for causal sets. They don't just say, in causal set theory, one usually says just pick these space-time events at random. But now we're saying, no, we actually have a generator. Our machine code produces an actual distribution of where the events go in space-time. And that then automatically leads to relativity and a bunch of other things. But you can use some of the methods of causal set theory then, which has been used to dealing with random distributions of events. Now we have sort of algorithmically generated distributions of events, but you can go ahead and use some of the machinery to go and look at what we're doing from there on out. And that was actually very useful to us in doing these things like black holes and so on, of being able to have essentially a sort of a template for creating space-time initial conditions that came from causal set theory ideas. We can then remove the template and just run according to our models. But if we say, how does it look initially, it's good to have that template to start from. Okay, so categorical quantum mechanics. So let's see. So the idea is we have this multiway graph, and we can think of this multiway graph as at sort of a mathematical level. Let's see, how deep do we want to go in this? So category theory, for people who don't know it, is kind of an attempt to have sort of a global framework for thinking about mathematics. At some level, when you're working at the level of individual axioms, individual expressions, and so on, you're dealing with sort of a machine code of mathematics. You're dealing with sort of individual tokens in mathematics. And for example, you might be dealing with individual elements of a group, individual groups, things like that. But what category theory does is it says, let's just deal with objects, which are whole lumps of sort of all possible groups and certain features of all possible groups. And that's category theory is dealing with these whole sort of aggregated lumps of things. It's sort of far above the machine code of mathematics, dealing with kind of the sort of framework level description of mathematics. Okay, so category theory in more specificity tends to deal with, within a category, there are objects and there are morphisms, which are mappings from one object to another and so on. And that has an appearance that's very much like a graph. It's like object connected to object, connected to object, and so on. And that kind of structure is very similar to the structure that we see in our multiway graphs. It gets a little bit more elaborate in these things called monoidal categories, whose name I hate, sort of relate to things where it's not just a function of one variable going to a function of going to a single thing, but two variables in, two things in, two things out, or multiple things in, multiple things out, and so on. And in any case, there's a way of understanding our multiway graphs in terms of higher category theory. Let me not. And basically, the point is that there's a way of representing kind of what happens in these branchial layers in our multiway graph in terms of the kinds of constructs that have been used in categorical quantum mechanics. And then those constructs, particularly a thing called ZX calculus, is an approach to doing this, where those constructs can be, you can make a mapping between those constructs and the standard formulation of quantum mechanics, but then those constructs very directly map into our multiway graphs. Okay, what does this mean? This means in practice, you can actually take something like a description of a quantum circuit, that, a standard thing. We've got a nice new framework in Wolfram language for representing quantum circuits. And you can take a description of the quantum circuit and you can compile it into a multiway graph description through categorical quantum mechanics, through ZX calculus, and so on. You get something where just in terms of the multiway graph, there is a description of kind of the underlying structure of that quantum circuit. And then what's neat, and this is Jonathan plus Xerxes Asawala and Mano Namaduri's work on taking this sort of formalism of categorical quantum mechanics and using it as a practical way to take quantum circuits and actually compile from a quantum circuit down into our models. So once again, just like in the case of general relativity, where we can compile a structure of space-time into this hypergraph, we are compiling a quantum circuit into something represented in terms of multiway graphs. And you might say, so what? Well, it turns out that we can then use theorem proving techniques at the multiway graph level and actually produce, it seems, better, more efficient optimizations of quantum circuits than it's been possible to do before, by using basically the much clearer machine code structure that we now have underneath quantum mechanics, rather than using the standard formalism of quantum mechanics. But one of the things that this means is, just like in the case of general relativity, we can have sort of a proof by compilation. Yes, we really reproduce quantum mechanics because you can take something that's been formulated in sort of quantum information theory terms and just compile it into our multiway graphs and do computations at the multi-way graph level and see that you get the same kinds of things. So for example, there's a sort of formal proof of quantum teleportation that you can start to make through the multi-way graph. You can also ask questions about quantum computing and what's going to happen there, and what happens when you sort of compile a quantum computing operation into the multi-way graph. What do you get to see about what happens? We've been able to do some of that. That's certainly not a finished story. But one of the things that you realize in our models is that you get to understand not only the process of sort of parallelizing everything through all these threads of history that seems like the quantum advantage, you also get to understand something about the process of measuring that quantum process and sort of corralling all those threads of history back together so that the poor computationally bounded observer, that's us, can conclude that something definite happened. And so there's sort of a big question about how much effort does it take to do that corralling back relative to the oomph that you get from being able to run things in parallel. We don't know the answer to that. It's not, I think, looking that good for quantum computing. It's something I've kind of suspected since like 1980 or so, that there will be this kind of problem for quantum computers, but 1981 maybe. But it seems like that's what's actually playing out here. But the reason we're able to see this is because we have something much closer to an honest model of measurement. We actually have the process of measurement is represented in terms of, for example, Jonathan's sequence of completions. I should explain that, in a sense, the completions are merely a speed up. They're merely a way of us concluding in a limited time that the universe has a definite form and being able to say definite things. If we were to wait long enough, and if we have causal invariance, then everything will eventually resolve. And that's why it's possible for us to have a point of view that involves, oh, we just say this is equivalent to this and equivalent to that. It could be we could say this is equivalent to that, and you could say, well, that's all very nice, but it's not consistent. You could have different sort of completions that you do, and they could end up with completely inconsistent results. It's a consequence of this causal invariance that won't happen. That in a sense, the completions are a way of speeding up, or a way of us concluding we can have definite things to say about the world without having to sort of wait for everything to resolve, so to speak. And that's kind of a way to understand what's happening. So in some sense, the fact that we're concluding these definite things about what's happening in the world is a consequence of sort of just our point of view. It is not it's something that we are pulling together, so to speak. Okay, so let's see about quantum mechanics. Well, there's lots of things to talk about sort of implications of our models for quantum mechanics. The question of fermions versus bosons, for example, we have some ideas. We have not concluded that yet. It's looking like the likelihood is that bosons are associated with essentially two-way branch shield graphs, and fermions are associated with essentially one-way branch shield graphs in some sense. That in a sense, the fact that bosons like to kind of get together as a consequence of kind of the way that they're associated with merges in the multi-way graph, and fermions are associated with branches in the multi-way graph in some sense. And that's our current view of, and one of the things that looks like it's going to be the case, again, quite a remarkable thing, is that we're going to be able to talk about fermionicity in the bulk and bosonicity in the bulk without having to talk about individual particles. So it looks like we're going to get a handle on this, and that's one direction. Another question, as we start to think about particles, is how do we identify kind of these topological obstructions in our models? Well, part of the issue is we have to be able to identify sort of symmetries and features of our models to begin with. So, for example, even rotational symmetry is not trivial. And I should explain that in our models, as we think about hypergraphs and all these kinds of things, one of the big things we have to do is generalize the whole stack of ideas that build calculus and analysis. Because that stack of ideas, people learn univariate calculus, they learn multivariate calculus. That means you've got one variable, or you've got 1, 2, 3, 4 variables, or whatever. You've got a certain number of variables, and you're looking at the variation of functions as you change the values of those variables. Well, in our models, what we have is something below the notion of a variable. What we have, in a sense, if we had this whole sort of grid of, if we could coordinate everything on a nice grid, we might say one direction in the grid corresponds to one variable, another direction in the grid corresponds to another variable. But what we have instead is this hypergraph that doesn't have that kind of coordinatized grid structure. So we don't get to talk about variables as such, as a fundamental thing. What we have as a fundamental thing is something much lower level than that. All the things about variables and all the features of tangent spaces and all these kinds of things that are the things that make calculus and analysis, they all have to emerge from our models from something much lower level. And by the way, we can immediately see there's a problem because a lot of the concepts of things like differential geometry have never been defined outside of interdimensional space. But our spaces don't have to be interdimensional, so we know already there's an issue. So we have to build kind of a hypercalculus that is sort of a generalization of calculus that describes what happens from these things that are in a sense lower level even than variables. We have to define what tensors mean. We have to define what all these kinds of things mean. And that will give us a notion of where we have an understanding, we think, of how manifolds arise, how things that are locally like Euclidean space arise. One of the things that's a question is how internal symmetries, how symmetries arise. How, for example, you start at a point in the hypergraph and you're looking at all possible paths away from that point. How do you compare the different paths? That would be like saying you start at a point in space and you look at all different directions from that point in space. How do you compare those directions? And you say, well, they have rotational symmetry, for example. What's the analog of that in the hypergraph case? The analog of that is that all these different possible geodesics from a point, we have to say what their relations are. And in a sense, the continuum limit of that, we hope, is something like a Lie group, a continuous group that represents kind of it'll be an approximation to that continuous group that represents all these different possible directions of this path. Okay, so that whole story segues into a story about things like spin and angular momentum and so on. It also segues into a story about local gauge invariance. And it's this, there's the thing, we've started to explore this, we've made some progress with this, of exploring the relationship. How do you pack this sort of local internal rotations together with sort of external spatial rotations and pack that all into our hypergraph? And how do you kind of have the sort of the weavings of this hypergraph correspond to, in some slicing of it, you're seeing things that happen in physical space, and some aspects of the details of what's happening inside relate to kind of sort of internal symmetry attributes and so on. And so one big question is, when we look at those internal symmetry attributes, what kind of limits can we get? In the case of, we know that we can get, in the case of physical space, that we can get things which limit to Euclidean space and so on. We don't know how many dimensions and things like that, but we can kind of know that it can be Euclidean space. In the case of these internal things, what does it limit to? What kind of Lie group structure does it limit to? Can we say something about the types of Lie groups that can arise as internal symmetries? That will be very significant because we know from the standard model of particle physics, we know that the actual Lie groups that correspond to the gauge groups in particle physics, we know it's SU3 cross SU2 cross U1, but that is part of things like the E8 Lie group. And we know, and the question is, can we see that it is inevitable that a certain family of Lie groups have to be the thing that arise as this limiting internal symmetry in our models? So that's something we don't know yet, but it's something we're very interested in. Now, it turns out a sort of a big story associated with particles and spin and all these kinds of things. It's actually surprisingly like vortices and fluids. Vortices and fluids have stability because when you have fluid that's always going around the circle, you can't continuously deform that circle to nothing. You can move the circle around and elongate it and so on, but you can't get rid of the fact that it's looping around. So that concept is a concept of homotopy and a mathematical concept. And that's something, so one of the directions that we're studying a lot is kind of the relationship of our models to various questions, various sort of homotopic questions. And this sort of the relationship between paths in our models, not just a point-to-point story, but a path-to-path story. How does that work? What does it mean when there's something that prevents you from deforming one path into another? And it seems like that's going to be related to a lot of these questions about things like spin and internal symmetries and so on, but it's not yet worked out. So that's something we're actively interested in. So let's see. So that was a little bit on sort of the quantum mechanics story and quantum mechanics and beyond. There's kind of this big relationship between quantum mechanics and general relativity that happens in connection with black holes and so on. And in particular, one of the things that's been an excitement in physics in general is this holographic idea that there's sort of a correspondence between general relativity kinds of things and quantum kinds of things. So in our models, we're beginning to see where that really comes from. It's a relationship between physical space and branchial space. And I already mentioned some of the correspondence, like between the Einstein equations and the Feynman path integral, between physical space and branchial space, but there seems to be more than that. It seems like when you have this multi-way graph and you're looking at kind of slicing it, looking at how things progress in time versus how things are sliced across in branchial space, that one of them is a sort of foliation, a succession of leaves in time. Another is a fibration, looking at the fibers of what happens as you go down through time. And there's some relationship between these foliations and fibrations that probably is what gives you these kinds of ideas like the holographic principle. And so the holographic principle is a story of the correspondence, I think, in our models between physical space and branchial space. And so that's and there are many detailed features of that we're just starting to explore. It's what's really nice is the extent to which we can leverage what's already known in the work that's been done in mathematical physics, and the extent to which what we can do can provide sort of concrete illumination of how those kinds of things work. So let me, so that's kind of a little bit of a summary of, I'm probably forgetting some important things of where we're at. In kind of quantum mechanics, we're able to do this sort of compilation of quantum information theory down to multi-way graphs. That's pretty exciting because it gives us both a practical way to do quantum information theory and sort of proof by compilation about our models. In quantum field theory, we are at an earlier stage, but the big thing that is a potential is to be able to do essentially quantum field theory from the ground up. In quantum field theory, it's very hard to do actual computations. It has been very hard to do computations. You have to kind of cheat and rotate time so that it behaves just like space and do all kinds of things in lattice gauge theories and so on. It's all kind of messy. In our models, there is the potential to do the same kind of thing that we did for the Einstein equations, to actually go directly from this underlying hypergraph rewriting multi-way graph story and actually reproduce explicitly kind of quantum field theory. Now, to get to quantum field theory in our actual universe, we have to go many orders of magnitude far beyond what we can go, but there's at least a decent chance that, just like in the general relativity case, we can already see important effects of quantum field theory and do quantitative computations by going only a small distance sort of up in terms of scale size from this sort of underlying elementary lengths and so on. So that's kind of a coming attraction, which will be very exciting if we're able to actually finally have a way to do more effective computations in quantum field theory using the underlying sort of machine code of our models. In a sense, what's happened in the traditional approach is we're starting from this high-level mathematical description, which our models don't deny. It's just that our models provide the machine code from which that high-level description can be produced. And that high-level description is just not a very efficient place in which to work to actually do the computations. So, okay, so that's a little bit on some of the things that have been going on in sort of the physics side of this. There are questions about how can we do experimental investigations of everything we're talking about. I mentioned some things about dimension fluctuation, exotic structures in space-time. There are a bunch of things in the cosmological domain. There are a bunch of things in kind of black holes that are hanging by a thread, so to speak. There are also things in the quantum domain. I think the most significant feature of our quantum story is the following thing. In physical space, the limitation on information transmission is the speed of light. In our models, there is a necessary similar limitation on the speed of information transmission in branchial space. It's a maximum entanglement speed, we call it zeta. And it is the maximum rate at which you can essentially measure more things in the maximum rate of motion in branchial space, the maximum rate at which you can measure more quantum degrees of freedom. And it's a maximum entanglement rate. And we don't know its value. There is one free parameter in our models, one fundamental free parameter. And you can move it around to lots of different places. You can say, what is the elementary length? Is it 10 to the minus 93 meters? Is it something different? You can say, what is the maximum entanglement speed? You can move around this question there's one free parameter. We don't know what its value is. We have a few guesses, but they may be way off. They may be off by 100 orders of magnitude for all we know. But in the guesses that we have, the maximum entanglement speed will be about 10 to the 5 solar masses per second. It's in weird units because of the way quantum mechanics works. And so that, in a sense, is telling us the maximum rate of motion in branchial space, the maximum rate at which, just like in physical space, there's a maximum rate at which we can explore new space. It's the speed of light. In branchial space, there's a maximum rate at which we can explore new quantum degrees of freedom. It's this maximum entanglement speed. And by the way, just like there is time dilation, for example, in special relativity, when you're exploring space, you kind of have a trade-off. If you want to see what's happening in the universe, you can either say, I'm going to sit in one place and I'm going to let time progress and things are going to happen at a certain rate. Or you can say, no, I'm really very, I'm keen to move around. I'm going to move in space, but I get to use some parts of the computation that is me is used to service my motion in space. And that leaves fewer amounts of computation to do progress in time. And that's why time dilation happens. In a sense, what's happening in time dilation is you're using you get a certain sort of budget of computational operations. That is your experience of time. Your experience of time is the inexorable process of a certain number of steps of computation. And you can use those steps of computation to do different things. You can use them to just see how the universe progresses, or you can use them to move around in space. And if you use some of them to move around in space, you get to use fewer of them to see how the universe progresses. And that's why time dilation happens. And by the way, that explanation of that sort of mechanical explanation of time dilation, that's something very new in our models. There's never been kind of a way to understand sort of mechanically, in a sense, why time dilation happens. But the same thing happens in quantum mechanics, that there's a similar time dilation. If you essentially measure too quickly the quantum Zeno effect, you expect that time will effectively progress less rapidly. And that's something, there's some experiments on that have been done. And possibly there are ways to use our maximum entanglement speed to be more quantitative about those experiments, and possibly to sort of home in on measuring the maximum entanglement speed. The maximum entanglement speed may also be related to some decoherence times in quantum computers and other things like that. And it might be possible to measure it that way, although it may be far out of range in terms of actual magnitudes. It's also probably the case that in some black hole processes, the maximum entanglement speed, so the merger of black holes is limited by the speed of light, but it's also going to be limited by the maximum entanglement speed, and that might be something that will be observable on a short time scale. So, okay, so let's see. So we talked a bit, I'm thinking about other, there's a long list of other potential ways that one can sort of suggestions that our model makes about things that you might be able to observe in physical experiments, like these things called oligons, particles much lighter than electrons, things like that. There's a whole bunch of these kinds of things. I wrote down some of them. I wrote a piece today about sort of summarizing our first year, where I give kind of a list of some of these different potential experimental implications. But it's worth emphasizing that every one of these things, there's just a lot of actual physics to do to relate the sort of the underlying machine code expectations with what is actually observable in a telescope or whatever else. Even to know how does a photon propagate through a 3.01 dimensional lump of space. We don't really know that. We don't know how that works. That's a piece of classical electromagnetism, well, albeit a little bit non-classical because it uses hypercalculus, so to speak, to deal with this 3.01 dimensional space, and we don't know how that works. But it's sort of a traditional physics calculation that has to be done to try to work out what's going on there, and then we can actually do measurements. But there are already suggestions of things you might see that you could start looking for, even though you don't know the orders of magnitude of actual effects and so on. So, okay. So another thing that's happened with our project is something that, again, I didn't really expect, which is to be able to go beyond, to be able to take the formalism of our project and apply it to areas that are not just fundamental physics. And that's very important and interesting because it, as a practical matter, provides a different, just gives one more mileage for this formalism. But it's also important because we get to, as we apply the formalism to metamathematics or to distributed computing or to chemistry or whatever else, or to economics, we get to import all of the intuition and all of the results that have been gotten in 20th century physics, for example, all of the sophistication of mathematical physics, we get to import it into a field that has never had that kind of sophistication. And we also get to take the intuition of these other fields and take them back to physics. I mean, I already mentioned talking about automated theorem proving as intuitional inspiration for some of what's happened in physics. And that's something a very different field, which is, relates to the same formalism and so on. By the way, before I get to that, maybe I should mention another kind of more philosophical point that I was looking at recently. It has to do with how does consciousness relate to what we're talking about? I'd always kind of batted away any discussion of consciousness. I thought not scientifically discussable, don't know what the term means, all a big mess. But I had realized a long time ago that the whole story of sort of computational sophistication, computational irreducibility, this is when we think about something like life or something like intelligence, we have particular definitions of those things based on our experience of here on Earth or with humans or whatever. But if we try and think about what's the generalization of life, what's the generalization of intelligence, what's the abstract definition of those things, we wind up finding out that we're basically talking about it's just sophisticated computation is going on. And it might be computation that we can readily understand. It's like what an animal does or something, or it might be computation that we don't readily understand, like what the weather does, where we don't know what the purposes of the weather are, but yet we can say it's computationally as sophisticated as what happens in our brains and so on. That's a consequence of this thing I call the principle of computational equivalence, which I'm not going to get into a big discussion of right here. But in any case, the result of sort of exploring the computational universe, learning about this principle of computational equivalence, was kind of this understanding that the generalized versions of life and intelligence are in a sense merely sophisticated computation. And I'd sort of assumed that consciousness was another step in that same chain, but it isn't. Instead, it's actually a step down from general sophisticated computation. I think consciousness is a story of the fact that we perceive a definite thread of it. We have a definite thread of experience. Time is very important. We perceive a definite sequence of things to have happened. We sequentialize our experience of the universe. We try and put it into a single thread of experience where we have a memory of the past and so on. And the thing that I realized is that sequentialization, that kind of corralling of that description of the universe in terms of this kind of thread of experience, that I think is the essence of what what consciousness kind of adds to the picture. And by the way, it's what leads to the kind of the very way that we perceive the universe. So in other words, what we have done with our consciousness is we are experiencing the universe through this thread of experience. We're sequentializing our experience of the universe. If we look at everything that's happening in the universe, all those atoms of space, they're all doing their thing all over the universe. All sorts of different things are happening. That's not what we understand. We are merely computationally bounded observers who have this feature that we are generating a thread of experience. As soon as we generate that thread of experience, we're just slicing, we're taking a particular sampling of everything that's happening in the universe. And that particular sampling has various features. The point is that because of the computational boundedness and the sequentialization idea, we are taking certain samples that correspond to essentially reference frames for reading the universe that are the things, and in those reference frames, the things we conclude are happening are the things that the laws of physics tell us are happening. So in a sense, we are, in a sense, responsible for our laws of physics because it is our computationally bounded, sequentialized experience that we might think of as our consciousness that is what drives the fact that we observe certain laws of physics to be the ones that are happening. And then many things going on in the universe which we are completely unaware of, which our consciousness does not lock into, so to speak. It's just like molecules of gas in the room, they're all bouncing around in complicated ways, but all we measure is the pressure of the gas. And it's the same kind of thing with our experience of space, our experience of the collection of quantum histories and so on. We are experiencing just this sequentialized thread of these things. And it is within that sequentialized thread that we observe the laws of physics as the laws of physics seem to be in what we've discovered in 20th century physics and so on. And so this is both an understanding of sort of the role of consciousness and its role in driving the laws of physics, so to speak. And so you can ask questions about whether there are alternatives. I mean, if we were the size of planets or the size of atoms or something, or we had other different sensory systems that, our brains didn't work slowly compared to the speed of light, things like that. How would we have it constructed? Kind of what would have been our construction of our view of the universe? And the answer is we would have ended up with, I think, very different laws of physics that describe the universe in an utterly incoherent way. And that's part of the story of these rulal reference frames and so on, and part of the story of sort of when we meet the aliens, so to speak, in quotes, we've always assumed that at least they live in the same universe, they have the same physics. That isn't really true. They can exist in they can be using a different rulal reference frame, have an utterly different description of the universe that would be coherent were we to look at the level of individual atoms of space. But the level of sort of the sampling of the universe that we take, it just seems utterly incoherent. It seems like it's just a bunch of dust, very microscopic dust relative to the very concrete things that we imagine are happening in the universe. So that's sort of another thing. There's another thing that I've just been working on about sort of why the universe exists. And I think that it's a very interesting story of kind of rulal reference frames and things that I think will actually give us a credible scientific answer to that question that I've just been working on. So, okay, so those are some of the things that. Oh, and by the way, this idea of sequentialization being the sort of an essence of consciousness. One of the things as a practical matter in doing computing. One's been interested in doing distributed computing, parallel computing. Lots of different computational operations happen all in their own time, not in sequence, so to speak. And it's been very hard to wrap our brains around that process. I've been trying for years to be able to have good description languages for distributed computing. It's been really hard. I think I now understand why. I think it's because our fundamental existence, our sort of fundamental perception of the world, our fundamental consciousness is tied into this idea of sequentialization. And when you're doing these distributed things, that's fundamentally not dealing with that. And so you have to start thinking about sort of programming in certain reference frames and so on. You have to start seeing how do you corral that distributed thing into something we can understand. And it's something which is fundamentally at odds with kind of our type of sequentialized consciousness, so to speak. Okay, so one of the things that I was mentioning is the formalism that we have of all of these multiway graphs and spatial hypergraphs and all these kinds of things. That is a formalism that in a sense transcends talking just about physics. In the past, I had a lot of experience with cellular automata, which are very simple programs where you just have a line of, let's say, black or white cells. You just have a rule that locally updates the colors of those cells based on neighboring cells. Cellular automata are, in a sense, absolutely minimal models where space and time have been predefined. You've got this lattice of cells, they evolve in certain steps and so on. They are a minimal model of that. And one of the things that's been interesting in the time since the early 1980s when I started studying cellular automata is how unbelievably diverse the applications of cellular automata have been. They're sort of minimal models of parallel computation, and they apply all over the place to road traffic flow or leaf behavior or all kinds of different things can be modeled with cellular automata because they are minimal models. They're a minimal formalism for describing sort of space and time determined parallel computation. Okay, so similarly, our new models are sort of minimal models for systems where there are events that can happen at any moment and that don't have a predefined order and that operate on some kind of underlying structure like a spatial hypergraph. I studied this year, because it was the centenary of them, these things called combinators, which don't work using a hypergraph, they work using a tree-like structure, and they're kind of an alternative universe that doesn't work with that would have kind of tree-like separations as well as the space-like separations of standard physics and so on. But in any case, the point is that the formalism that we have, particularly around multiway graphs, is a tremendously general thing that can be applied in all sorts of places. And so we've been looking at a number of places to apply it. One that I've been particularly interested in is metamathematics. I mentioned before that you can think of kind of the progress of mathematics, the proving of theorems from other theorems, as being like these kind of events. An event is like applying some axiom or applying some lemma to go from one theorem to another. And so you build up this whole network of theorems. And I looked this year at Euclid and the network of theorems that he'd built. In a sense, what he was doing was there is an underlying possible network of theorems that is sort of defining an underlying structure of metamathematical space. And what Euclid was doing is saying, I'm going to make a city, so to speak, at this. I'm going to populate this particular point in metamathematical space, and I'm going to say, this is the theorem I'm going to write down in my book. And so in a sense, there's this underlying space of the structure of all possible theorems, and then there is a human geography of where do people actually place the theorems that they have studied. And just like in the case of population sort of cities on the Earth, you could discover that the Earth is a sphere by looking at distances between cities and so on. So you can discover things about the structure of metamathematical space by looking at the populated places in metamathematical space, which are, for example, the 3 million theorems that people have published in the literature of mathematics. But what we've been interested in is what I've been particularly interested in is kind of this underlying structure of metamathematical space. What does it look like? And what then the human geography of mathematics, how does it sit on top of this underlying structure of metamathematical space? And so one of the questions is, if these underlying sort of propositions in mathematics are like the atoms of space, what is the analog of relativity, for example, in mathematics? What is the large-scale description that goes above these microscopic descriptions? And there are efforts to formalize mathematics, in which something like the Pythagorean theorem might consist of 10,000 or 100,000 underlying sort of atomic propositions of mathematics that are much lower level than something like the Pythagorean theorem. In a sense, the Pythagorean theorem is the sort of human level version of mathematics, far above this kind of underlying atomic version. And so the question is sort of, what is the emergent structure? And then to what extent can you apply ideas like relativity, for example, to think about metamathematical space? What is the analog of, the geodesic in metamathematical space is something about a shortest proof, the sort of motion in mathematical space, the progress of time is sort of the mathematics that's getting done. The question is, what's sort of the limit of mathematics? This is related to sort of what is the true nature of mathematics and what is human mathematics as opposed to all possible mathematics. One of the things that's been a surprise to me is that when you sort of pick mathematical questions in some sense at random in the computational universe, you often end up with undecidability, and your kind of Gödel's theorem is rammed in your face, so to speak. Whereas in doing practical mathematics that humans do, that doesn't happen very often. So there's something different about the sort of human experience of metamathematical space and what's underlying metamathematical space. And I think it's the same kind of thing that's happening in physical space, that our experience of the universe and all these little atoms of space is different. Our sort of aggregated experience is different from that microscopic experience. And I don't know whether things like category theory help us to describe kind of that sort of aggregated appearance of mathematics. That's the human version of mathematics as opposed to the raw mathematics. So that's a direction in a field very different from physics. By the way, the one of the things that happens is this. When we ask about sort of all possible rules, and we're applying all possible rules, we get the thing we call the rule multiway graph, which is this sort of structure that you get from sort of following all possible rules. The rule multiway graph seems to be a concrete version of something that has been explored in mathematics, in higher category theory. It's a concrete version of the infinity groupoid of Grothendieck and so on. It's this representation of this sort of ultimate limit of sort of applying more and more morphisms between morphisms, mappings between mappings, and so on in category theory, leads you to this infinity groupoid, which seems to be the same object, this same rule multiway system that shows up in our ideas about physics. And there are conjectures about sort of the inevitable geometry of the rule multiway, or the infinity groupoid, which becomes conjectures about the inevitable geometry of the rule multiway system, which is basically to say that the thing I was saying intuitively before, that when you run all possible rules, because those rules relate to each other, you get this very tangled up thing. And that very tangled up thing has sort of inevitable geometry. And that's what trickles down to give us things like the geometry of space and so on. And it will presumably trickle down to give us geometries of metamathematical space and so on as well. But it's interesting that sort of upper limit of abstraction in pure mathematics is sort of intersecting with what we're thinking about as the upper limit of sort of machine codeness of thinking about the physical universe. Okay, so we can even go beyond metamathematics. We can ask about other fields that we can think about in terms of this kind of formalism. Another one is distributed computing. I mentioned that a bit, where we're sort of thinking about how to, in practice, how to humanize this kind of distributed process of computation that's analogous to the distributed process of computation that seems to happen in the physical universe, and to be able to say, oh, you've got this fork here, you've got this race condition here, that's like event horizons, that's like the uncertainty principle, being able to make these sort of physicalized analogies, because then we get to leverage this amazing amount of intellectual work that's been done in mathematical physics. We get to leverage that to get an understanding of distributed computing. And similarly, we get to say, oh, what does the CAP theorem of distributed computing have to say? What's its analog in physics? And one of the things that we've done a lot of this year is making these analogies between these different fields. For example, one of the things I've been interested in is in quantum mechanics. There's the question of this multi-way graph and all these different understandings of the multi-way graph and how that works in quantum mechanics. What are some sort of everyday analogies to that we can think of using the same formalism? So for example, game graphs. If you're playing tic-tac-toe, then you have a particular game state, and there are multiple game states that you can get to from that game state. The thing you build up is a multi-way graph. And I think that there's a way of sort of thinking about the scoring of games and you only care about who won and who lost as being analogies to the way quantum measurements works. And one of the points of doing that is both that there's certain results in the theory of games and so on, but also that it kind of humanizes, it gives us a more intuitive sense of what's happening in quantum mechanics if we can talk about it in terms of something we somewhat experienced in terms of games and so on. And that kind of leads us to questions about other ways that we can use this formalism. So another direction that we've been going in is making a kind of distributed version of blockchain that makes use of our formalism. So in a sense, blockchain, where you have a single ledger that you're accumulating, is kind of like the sequentialized consciousness story of, and in the end, you need, for the operation of the world, you need a certain amount of sequentialization, and you do all these transactions, and there might be sort of quantum uncertainty about what happened in those transactions. But in the end, somebody bought the car and is driving it off the lot, so to speak. And that's like the sort of quantum measurement of something definite happened in the end. But so what we seem to be able to be doing is making this kind of distributed blockchain that is based on essentially quantum ideas. That it's nothing quantum mechanical about it, but it's based on the same formalism that we're using for quantum mechanics to understand how that works and to make something quite practical. And I think that the one of the things that I kind of like about that, in addition to the fact that it's kind of a useful thing in the world to have such a distributed blockchain technology, one of the things that's kind of nice is that, at the point where people are saying there's sort of a quantum uncertainty in their bank balance, so to speak, is the point where people begin to have a much more intuitive, much more internalized, humanized understanding of quantum mechanics, because we're not usually used to things behaving quantum mechanically in the world. That's something only the physicists can see, so to speak. Whereas the everyday person, if this is something that is a core piece of the sort of transaction system of the world and so on, it's something everybody gets exposed to. We get a very sort of humanized understanding of the essence of quantum mechanics. So that's one of the consequences of that. So we can look at other fields. Another one I've been interested in is chemistry. So in chemistry, you imagine doing chemical reactions, and that's like these events that produce different branches in a multi-way graph, because it's like you have one chemical and you can do 3 different things to it and you get 3 other chemicals, and that builds up this graph, and it's one of these multi-way graphs. Now, most of synthetic chemistry consists of trying to drive a particular path through that multi-way graph, get the best yield you can of a particular chemical going through a particular sequence of 30 reactions or something. But what if you look at the whole multi-way graph? What if you try and think about, let's say you were trying to make a molecular scale computer, and instead of saying that you would just look at this particular sequentialized program, you say, I'm going to take the whole multiway graph, and I'm going to think about that as being the computation. One of the things I looked at this year was multi-way Turing machines, sort of very minimalized multi-way computation systems, and trying to understand kind of what it means to be a universal computer in the world of multi-way Turing machines. Non-deterministic computation, so a standard Turing machine just does a particular sequence of operations, gets a definite result. A non-deterministic Turing machine is like kind of a multi-way Turing machine, except you're saying, I just want to pick one path. But in the multi-way case, you're saying, I'm going to look at all paths. I'm going to do the same kind of thing quantum mechanics does. I'm going to look at that whole bundle of different histories, and I'm going to tell you something global about that bundle of histories. It's a little bit different from non-deterministic computation, where you're picking out, you say, is one path the winner, so to speak? Like in NP problems, it's like, I just want one path that's going to do it. By the way, I might say that our kind of Rullial multi-way graph and so on seems to have relations to the whole P versus NP question and the geometrization of P versus NP, a whole separate discussion. But in any case, the thing, so in this kind of multi-way Turing machine, it's like we're doing a computation, but it's this whole bundle of results that we're getting. And I don't quite understand how to do computations in that sense. But if I did, then we would be able to think about them in terms of chemistry, in terms of not just saying, I want to get this one product, but I'm going to get this whole bundle of products. And then I can do another thing that's another, taking this whole bundle of products and turning it into something different. And that I think has the potential to make a quite practical molecular scale computer that is operating using multi-way computation. But then we have to do just the same thing we do in quantum mechanics. We have to make the analog of a quantum measurement to say, yes, this bundle of different things happened, but now we want to know what's the definite result that we as sequentialized consciousnesses care about deducing. And so then we pull that out, and that's kind of the result of our molecular scale computation. Now, I might say that I think one of the things that's been sort of a long time mystery in science is what's the right conceptual model for molecular biology, for systems biology, for kinds of the kind of, we biological organisms are the one shining example of kind of molecular scale computation. But we don't have a good picture, a good global picture of how it works. We do understand genomics to the point where we know there's sort of a digital representation of the programs that make things, but what those programs really do, yes, we have lots of diagrams of pathways and cells and all this kind of thing, and we can represent it in terms of systems of differential equations, all those kinds of things. But in terms of having a global picture of sort of how do you program in that kind of environment, how do we understand, how do we tell a story about what's happening in that environment? We've had trouble with that. And I think that if we can understand multi-way computation better, there is a chance that that becomes the paradigm that lets one understand kind of the operation of biology at a sort of molecular and systems level. So that's another kind of feature of sort of an application of our formalism. Another application of the formalism potentially is to biological evolution. One feature of sort of multi-way graphs is the crazy thought that just think about really all possible things that can happen. Don't worry about, oh, there's so many things that can happen, I have to take only this particular path. Just imagine you're looking at all of them. That's the multi-way graph. And now there's certain inexorable features of the multi-way graph and of slices of the multi-way graph, and that gives you sort of scientific results from that. Let's see, what fields am I forgetting? Another one I've been looking at a bit is economics. In a sense, this distributed blockchain story is kind of the way into that, because it's kind of like, imagine all the transactions that are happening in the world. There are all these little events that are happening. Then try to understand what the consequences of all these transactions happening is. What are the features? Well, one important feature is computational irreducibility. And I have this suspicion that sort of the invariant value of money has something to do with the kind of invariant properties of computational irreducibility. And then the question you can ask is, what are the kind of economic analogs of relativity, for example? What are the slices of computational reducibility that can be identified in economic systems, even when the underlying behavior and the level of individual transactions generates this kind of net of computational irreducibility? So that's another thing that I've been interested in that we're looking at. So, okay, a lot of different directions, a lot of different things, and I've been yakking for a long time here. let me just say a few things about, I mean, from my point of view, this project is just going great. It's going great in terms of physics. It's, when you have a model, kind of the big test of a model is, do you get out more than you put in? We've essentially put almost nothing in terms of what the underlying sort of structure of, oh, there's a 3 and a 7 and an 8 in these different places in the model. We don't have any of that stuff. It's just a structural description, a formalistic structural description. And yet we're getting out all of these things about physics, and it's hard work. We have to push sort of frontiers of mathematics and mathematical physics to be able to deduce these things. But nevertheless, we're progressively discovering these aspects of physics coming out of our models, and we're seeing that it's very beautiful. That these things that are kind of like, oh, fermions and bosons, how do they work? Well, maybe it's just because there are directed and undirected hypergraphs, and maybe this thing about holography is to do with this relationship between foliations and vibrations and things. It's very beautiful stuff, and it's in a sense, we live in a more beautiful universe than I would have given it credit for, in the sense that the sort of the pure abstract formalism that we can imagine is turning out to be the thing that plays and describes our physical universe. It's not a big hodgepodge mess where we're having to say, oh, it so happens it works this way and that way. And, we could imagine it was kind of like created for us because it's such a big, by in a giant simulation or something, because such a big mess of somebody wrote that particular line of code and so on. No, it doesn't work that way. It's a very beautiful, very abstract, very general, very inevitable kind of structure. And that's that's a remarkable thing. The fact that this formalism can be used immediately to do actual calculations in physics, that's really neat and not something I saw coming. The fact that this formalism can be used even outside of physics is something else that's very important. As I say, partly because of the actual things it delivers outside of physics, but partly also because this kind of trading of intuition, results, ideas between physics and other fields that gives more power both to physics and to these other fields. So in terms of the actual doing of this project, it's like, okay, you're going to find the fundamental theory of physics. How are you going to do it in the world? There isn't really a roadmap for doing a project like this. And so one of the things we've done is to sort of invent some pieces of that roadmap. A very important part is to make it a completely open project, to make it a project where kind of you can see into everything that's happening very transparently. And so we've been live streaming many of our working sessions when they aren't at too weird times of day and night and so on. We've been, so you can actually see Jonathan and me trying to figure stuff out or whatever it is about different kinds of topics. We've been uploading working notebooks, like the working notebooks I produce. They get uploaded mostly by the next day. And it's like what I worked on that evening. I've been doing the very bizarre thing of recording kind of video work logs of my actual process of working on things. One of the neat features of this is that if you see some result in something that I've written, well, first, the picture that I make, I have a rule. You have to be able to click it, copy it, and run the code, and should generate that picture. But also, if you want to, you can really drill down all the way. And you say, where did that come from? Well, I can find the actual moment in the video work log or whatever where that line was written. It's kind of like nothing is hidden. It's all kind of all transparent all the way down. And it's been very nice with the live streams we've had. We've had people following these live streams, making all kinds of suggestions, have given us some very useful references, very useful pointers that have been very helpful. I would say that so that's all been this kind of theory of open science. Nobody's ever done something like this before. And it's something, people ask me, should academics be doing this? Probably they should be. It's kind of, you have to have be a little bit gutsy to be prepared to actually live stream all of your mistakes, so to speak. But I think it's one of my features of having been around a while and having done a bunch of stuff is that I don't really care if it helps other people and it's interesting to people, then I'm happy to do that. It's I think that the thing that so this kind of very open approach to science. The other piece of this is our tools. So we use Wolfram language. That's the stack that I've been building for the last basically 40 years to enable what we can now do. And so that's what we're using to kind of be able to figure things out, both in terms of the practicalities of actually writing code, and in terms of the conceptual ideas of, oh, we understand how computation is organized because of all the work we put into the design of Wolfram language, because it gives us kind of this language for talking about things computationally. It's a sort of full-scale computational language that lets one talk about the world computationally, and by the way, seems to allow one to talk about the whole universe computationally, which is kind of an added bonus. But in any case, so one thing we've been doing is taking the functions that we create in Wolfram language that have been useful for our project, and now I don't know what it is, a couple of hundred of them, I think at least, are in our function repository, so everybody can use them, and there's source code there and all that kind of thing. It's been very, very nice to see that people who've been working on this project are making use of those functions. They're really able to leverage what we've already done. They're not just taking what we wrote in a paper and starting from scratch. They're able to take the actual computational tools, and they're able to take a step from where we got to, not going back to square one and rewriting their own code or whatever else. They can understand what we wrote because not only are there words, but there's also code, and they can use that code. And for example, even things like the standardization of the colors for all these different kinds of confusing graphs that we have, the fact that people are able to make use of that immediately gives a considerable additional clarity to sort of presentations of things done with our models. Now, it's been great. The actual interaction with the world about this project has been really good. It's an interesting thing because 20 years ago, I kind of introduced some precursors of this as sort of a sideshow to my new kind of science effort of exploring the computational universe. And people were like, oh, we're not really interested in that. Well, I'm happy to say that 20 years later, we figured out a lot more, but also maybe the world has changed. Maybe our ways of delivering the information have changed, but the results has been very different and a very positive set of interactions. It's also helped that we've understood kind of the synergy that exists with existing areas of mathematical physics, but a very, very positive interaction with lots of different people in lots of different fields. I would say that if I were to give a sort of aggregate picture, I would say that the deepest interactions are happening in the more abstract fields, in things like higher category theory, in some of these areas of, some of the areas like graph rewriting, term rewriting, I don't know, topos theory, causal set theory is another one, but these various kinds of pretty abstract fields that have been sort of working towards mathematical physics, but haven't necessarily had a grounding in something that's really physics, so to speak. Those are the places where we're seeing the first, and in things like categorical quantum mechanics and so on, we're seeing sort of, I would say, the first really deep absorption of the stuff we're doing. Now, we've also been developing a group of research affiliates and so on working on this project. It's a good group of people. Many of them have come to us through the summer school we did last summer and the winter school we did at the beginning of this year. And we've also done a number of study sessions about the physics project. And we're going to be progressively doing more of these educational kinds of activities and so on. But we have this kind of group of research affiliates that's sort of the group that we are particularly interacting with, and we hope that will expand progressively over time as more people get involved and so on. And this is sort of a very positive direction in terms of exploring this science. Well, I've yacked for too long here. I mean, I will just make a few personal comments. I mean, I've had a long career doing all kinds of things that have been pretty interesting to me, at least. And I didn't know if this physics project was ever going to happen. I've been sort of thinking about it for 30 years. And the fact that it was able to happen is really exciting to me. And for me, it's kind of like there's this giant new collection of possibilities that just opened up. I thought I built this big tower of things with Wolfram language and a bunch of the ideas from new kind of science and so on. But now there's this great new vista that just opened up and so many things to do. And as usually the case in sort of these kind of new directions in science, there's a new methodology, there's a new kind of paradigm, and there's a lot of very exciting low-hanging fruit to be picked for maybe 5 years, maybe 10, whatever. But the thing that to me is sort of, my life has more or less been an alternation between doing basic science and doing technology. And one of the things that's sort of remarkable to me about this is that I thought I've done some science, and that's led me to invent some technology, which then becomes tools that then lets me do more science and so on. I've done that alternation about 5 times so far in my life. And I thought that this physics project was going to be an end of the road piece of that kind of alternation, because I thought it's based on a bunch of technology, which is based on science, which is based on technology and so on. But it's based on technology, but this is just basic science. There's going to be nothing that comes out of this that's technological. How wrong I have been. It's turned out that this, of all the different kinds of science I've done, this probably has some of the most immediate, most technological implications of anything. And so even though we thought we were building a fundamental theory of physics, and we thought if there was a technological application, it was building, starships 300 years in the future, no, actually, it's something where there's applications of the formalism that we've built very much here and now to lots of different fields. And that's something I very much didn't see coming. It's something where the applications of that formalism to thinking about distributed computing, feeding back into technology and so on, is something very much here and now that exists. So anyway, it's been an exciting year for me. I would say that personally, I have, if you look at my posts in my writings, collection, blogs, etc., you'll find a variety of things from the quite formal and technical to the quite historical and so on. There have been a couple of centenaries this year of combinators and of post-tag systems, both of which are kind of simple creatures in the computational universe. And I kind of felt a need to recognize their centenaries, so spent a bunch of effort on that. I thought, gosh, this is going to be a distraction from the physics project, but it's turned out that, for example, studying combinators has given me a bunch of new perspectives about the physics project. Studying tag system of a bunch of new perspectives about kind of the meta-mathematical approach to the physics project and so on. So even though they look like distractions, and even though I did spend a certain amount of time chasing down the histories of some of the people involved in those different areas, because I'm a person who ends up being interested in the history of ideas as well as the ideas themselves, it's turned out those distractions were actually contributed to the progress of this project. Although I have to say, I might have, we probably would have gotten to particles a little bit sooner if I hadn't been distracted with things like combinators and so on. But anyway, so that's kind of a little bit of a summary of where we're at from my point of view. And it's been great to see people's interest and enthusiasm for this project. By the way, don't forget there's now a membership program for the project where you can get cool swag. And, I realized I forgot to bring with me some of the swag that you can get now. But it's cool swag now, and even cooler swag to come in the future. So please join our project. Over time, we most of the work that's been done on this project, some of it has been sort of funded philanthropically by me, basically. But much of it is being done by people out in the outside world, in academia and outside of academia. I think that as this goes forward, there will probably be a need to have a somewhat more centralized kind of way in which to get at least some parts of the project done. In our company, we've been pretty efficient over the last 35 years in inventing systems for doing innovative things. And I think some part of this project probably owes its success to the application of those techniques, and some part of the future of the project, I think, can benefit from those. And that's something where we probably will try to develop kind of a more centralized approach to some parts of this project, for which we are basically going to rely on philanthropy to move that forward. So contribute to the project, both in terms of ideas, in terms of joining live streams and giving us suggestions, in terms of writing code for the projects that exist around our project. Max Piskanoff has a whole GitHub with lots of different project directions and so on, and there are lots of things to do for the function repository and so on related to our project. Join our various study sessions, summer schools, etc. We have another summer school coming up in a few months. I think the main thing I would say is that this is an early time in what looks to be an exceptionally promising direction in science. And knowing something about the history of science, people who get involved in these early times, somebody gets to be the Schrodinger, somebody gets to be the Heisenberg of this story, and that's that's something pretty fun, and it's a limited time opportunity because in some number of years, the low-hanging fruit will all have been picked. But right now, we're very much in a very rich kind of orchard of lots of fruit. Admittedly, some of that fruit requires standing on the backs of category theory and things like that to reach it, or so it seems. So there's a bit of technical sophistication involved, but it's still fruit that is it seems reachable in these times. Even though we also have to build a bunch of new mathematics, which hopefully will benefit pure mathematics itself. All right, I think that's everything I was going to say here. Let me wrap up, and I think Jonathan was going to make a few remarks as well. So over to Jonathan, the Associate Director of Research of our project and giant energy source for this project over the past year and earlier. Okay, over to Jonathan.
Okay, well, thank you very much, Stephen. That was I think you've done an excellent job of kind of contextualizing an awful lot of the stuff that went into the project and that has gone on over the last year. So I'll keep my remarks short. I won't comment much more on progress that's being made or projects coming in the future, because I think you've already covered that pretty well. The main thing I just wanted to mention were, I think it's worth picking out a handful of specific people who I think have really made, the last year that this project has been public, the great success that it has been. And so, and this is a combination of people who are kind of internal within the research group. They are people who are sort of semi-internal within the affiliate program. And then there are also people who are external, but who have been kind of instrumental in supplying us with ideas and kind of new directions of inspiration, or have helped us kind of to recruit bright young research affiliates or whatever. So at least on our side, I think I'm not going to be able to name everyone, so my apologies if I miss out anyone particularly egregious. And to make it even worse, I haven't made any notes, so I will probably forget someone very, very important. But okay, so at least on our side, I think one of the first people that needs to be mentioned is Xerxes Asawala, who Stephen I think has already mentioned a couple of times in his sort of opening. So I have to say, on a personal level, working together with Xerxes has been one of the most consistently pleasant and enjoyable aspects of the last year for me, at least. So to tell you a little bit, so Xerxes has kind of been our main sort of research manager type person. He's been the person primarily responsible for kind of organizing our research affiliates, making sure that they're working on useful stuff, being productive, producing nice papers, but also helping to coordinate our colloquia, our summer schools, our winter schools, our study sessions, etc. But even setting all of that aside, I think one of the key insights that's really come out of Xerxes being involved in this project is a radical philosophical shift in how we think about the model. So up until the point, up until last summer, when it was kind of really just myself, Stephen, and Max sort of working on this, we had all been thinking about a kind of bottom-up approach to thinking about the Wolfram model, where you start with discrete objects, you start with hypergraphs and things, and then you build up to these continuous, topological spaces. But when Xerxes came along, he kind of pointed out that there's this alternative way of thinking about the foundations of mathematics. So conventionally in mathematics, you think of the foundations in similar ways. You think about starting from set theory, starting from discrete stuff, and you build up to these higher things, these higher concepts like topology and analysis and so on. But over the last few years, as a consequence of some work in higher category theory, and also as a consequence of more generally this univalent foundations program of Voevodsky and others, there's been this other way of thinking about the foundations of mathematics that's kind of much more recent, which is that this whole homotopy type theory univalent foundations way of thinking, where instead one essentially goes from the top down. One starts from homotopy spaces, one starts from topological spaces. If you want to think about it in the higher category sense, one starts from an infinity groupoid, which is equipped with some notion of a topological space. And then if you want to construct something like a discrete set, you do so by passing to the discrete set of connected components of the space or something like that. And what Xerxes really was the first person to point out in a serious way is that we can think of the Wolfram model in a similar way too, right? Our rule multiway system, as Stephen mentioned, is a kind of model of at least a weak infinity category, a weak infinity groupoid. And so then if, under this hypothesis, under this Grothendieck sort of hypothesis, all of the kind of lower order objects, our multi-way evolution graphs, our causal graphs, our hypergraphs, etc., these discrete structures inherit spatial structure, inherit the structure of a topological space as a consequence, essentially, of this homotopy hypothesis. So it was a way of completely inverting our approach to thinking about what we were doing. It made all of these connections to type theory, to homotopy theory, to category theory, and even to areas like topological quantum mechanics that are based on similar formalisms. It was just a completely new rush of ideas that came out of that particular insight. And as I say, I think Xerxes was really the key person that made that idea happen. And so even setting aside all the other wonderful stuff that he's been working, Xerxes and I have also been with Mano, who I'll talk about in a moment, have also been working on this, categorical quantum mechanics stuff and so on. But even setting all of that aside, just that one key idea, I think, has now infused the philosophy of the whole rest of the project. It's certainly energized me. I think it's energized a lot of our other affiliates and researchers as well. And that's just an incredible thing that's happened over the last year. So while I'm talking about people responsible for kind of managing our affiliates and things, I also should mention Hatem Al-Shatlawi, who is our other sort of research manager, who's also, like Xerxes, has been involved in helping us to kind of to run things like our winter schools, our summer schools, our study sessions, and making sure that all of that runs smoothly, and also being a sort of a kind of mentor figure and general guru, particularly for our more junior research affiliates, for whom something like this is kind of it may well be their first experience of research, their first experience of writing academic papers, their first experience of speaking at conferences or whatever. And again, Hatem has been a really, really great influence in kind of in helping people get through, helping some of our more junior folk get across that kind of big emotional and intellectual hurdle. But again, just at a personal level, Hatem is, I think it's safe to say, one of the most relentlessly energetic and optimistic and energizing people I've ever encountered in my life. I mean, I think it's almost impossible to kind of go into a conversation with Hatem and not walk away feeling about 3 inches taller. And he's just he's a tremendous source of not just energy, but also very interesting ideas. He's a physicist, he's a technically sophisticated guy, but he's one of those rare physicists who's capable of genuine philosophical profundity and has very, very wide diversity of interests. And where, basically anytime I've had a conversation with him, whether it's about, foundations of quantum mechanics or metamathematics or, category theory or quantum gravity or biological evolution or whatever, I've come out of that conversation with, not just more energy, but actually, a fresh perspective on whatever that question was as a direct consequence of chatting with Hatem. And so, if working with Xerxes has been one of the best features of the last year, I think the opportunity to work more closely with Hatem is one of the things I'm most greatly looking forward to in the next year. And I think the final sort of internal person who I think is really worth mentioning is Mano, Manojna Namaduri, who I think, okay, the way I sort of think about this is my way of classifying people, different people are good at different things, right? So sometimes you meet people who are very, very good at this kind of big picture philosophical thinking, right? That they like big ideas and making connections between big ideas and connecting different concepts in disparate fields and using them to make sort of profound insights. And there are people who can really do that and understand these kind of big conceptual revolutions. There are also people who, on the other extreme, who are very, very good at understanding kind of deep, detailed technical and mathematical formalisms, and who can really understand, the precise details of a mathematical proof and know kind of what the detailed analytical assumptions or whatever that went into the axiomatic foundations of that particular argument were. Then you have people who are, to take another extreme, who are very, very good at implementing, at taking these kind of big picture philosophical ideas or these rich technical formalisms and turning them into, actual production grade usable code into efficient collections of zeros and ones that one can then perform simulations over or whatever. And generally speaking, you find people who are good at one of these things. Finding someone who's good at 2 of them is extremely rare, and finding someone who's good at all 3 is pretty much miraculous. And Mano is one of the very, very few people I've met who is genuinely good at all 3. And so she has been an instrumental part of, I know a bunch of the explorations and bulletins that Stephen has done, assisting with kind of the research side and with the kind of software development side. She's been absolutely instrumental in a lot of the stuff that I've been doing and that Xerxes and I have been doing on categorical quantum mechanics stuff. So like, the ZX calculus papers that we wrote, that the code for actually constructing ZX diagrams and sort of evolving them as multi-way operator systems, and then doing the theorem proving and the pathfinding over those systems, that was stuff that I kind of laid the foundations for. But Mano was really the person who saw those things through to fruition, and those are projects which probably wouldn't have happened, or at the very least wouldn't have happened in anything like as much in anything like the time frame that they did if it hadn't been for her. So those are three people, at least on our internal team, who I think we'd be remiss if we didn't mention explicitly. There are many other, we have various affiliates who I think have done absolutely wonderful things. A couple of examples that immediately spring to mind are Jorik Zeszka, who's been really a great influence in terms of sort of making connections between particularly our multi-way formalism and various concepts in theoretical computer science, looking at, and also beginning to make some connections to ideas in geometric group theory, sort of looking at growth rates of multi-way systems, particularly for strings, looking how they compare to kind of growth rates of groups, and also, looking at essentially the computability theoretic properties of those multi-way growth functions, starting to define essentially a general kind of algebra over those multi-way growth functions, and relating that to the sort of to the inbuilt algebraic properties of the multi-way systems themselves. And that's a thing which I think has great sort of potential mileage that I think also will connect wonderfully with all the compositional stuff and the category theoretic stuff that we've been doing recently. But the paper that he put out on the archive a couple of months ago on that topic, I think is already an amazing start. And given that he's a very junior guy, he's still a high school student, I think it's absolutely fantastic, the stuff that he's done there. There are others. Too many to mention, like Utkarsh Bajaj, who's currently kind of looking into some of the implications of discretization effects for kind of relativistic transformations of objects. Matt Kafka, who's starting to look at kind of statistical, using statistical mechanics, first principles statistical mechanics simulations to construct causal graphs and compare them against kind of causal structures that are produced by pure Wolfram model evolution, etc. I mean, I'm not going to name everyone. We have on the order of, I think, 50 or so sort of research affiliates actively working on the project, but there are some headline cases that I think are definitely worth pulling out there. And then the last thing I want to mention were people who are not sort of directly involved in the project, but who are outside, but who have been enthusiastic about what we've done and have been extremely helpful in kind of pushing our ideas forward. So one instance of that are people from the categorical quantum mechanics community that Stephen kind of alluded to. So they're particularly, especially Bob Cocker, who's been a greatly energetic sort of promoter of some of the ideas. I mean, just as we have been making use of various things that he's developed in CQM and in ZX calculus, he's also been kind of a great promoter of the stuff that we've been doing that relates to that. But also, other people, so Ross Duncan, who's also one of the co-developers of ZX calculus, Alex Kissinger, who's been a great sort of promoter of diagrammatic and developer of diagrammatic reasoning technologies, and has kind of pointed us to in various at least in the directions of various pieces of literature, and also has been an enthusiast of things like the PetriNet side of our project. People like Hector Miller Bakewell, who's helped us to kind of understand the connection between what we're doing with the CQM rewriting and concepts like conjecture synthesis. So lots of people in that general community, and also in the applied category theory community more generally. So Fabrizio Genovese, who's also been a sort of another consistent enthusiast of what we've done, is very interested. It seems to be seemingly very interested in getting involved, particularly, both in the PetriNet side and in the homotopy theory side. And we've had some very, very nice interactions with him. Even more recently, some nice interactions with people like David Spivak, who David in particular has helped us really understand this kind of graded monoidal structure that we get from our multi-way evolution graphs and our multi-way evolution causal graphs, which we were sort of quite uglily formalizing as a sort of category with two different monoidal structures. David proposed various ways of formalizing that as a double category or a bicategory or a weak two category and things, and those are all kind of interesting ideas that we're currently in the process of pursuing. So lots of great people out there in the sort of applied category theory community who I think we ought to thank. Another community that Stephen mentioned is the causal set community. So people like Tommaso Bolognesi, who's one of our affiliates, has been a long time advocate of the algorithmic approach to causal sets based on NKS methods, even long before the physics project really materialized. And also we've had very nice interactions with people like Faye Dowker. Faye, I should also mention specifically, I want to thank, as someone who has sent a vast number of students to our to apply to our most recent summer school. So I think at the last count, I found about 10 or so students from Imperial College London who had applied to our summer school, all of whom had said, oh, well, either directly or indirectly, that they'd been sent to us by Faye. So thank you, Faye, for supplying us with what looked to be a very, very lovely and interesting cohort of students there. Again, we've had useful interactions with David Rideout and others in that broader community. Who else have we got? There's people like Chiara Marletto, who is hopefully coming to give a talk at one of our colloquia very, very soon, who has been very excited. We met Chiara at this emergent space-time workshop that we did sort of towards that Stephen and I did and Xerxes towards the end of last year, organized by Paul Davies and Arizona State University. And there, Chiara showed great interest in kind of connecting the stuff that we were doing with our multi-way system formalism with ideas in constructor theory, and the general idea being that constructor theory is kind of a theory that operates at the level of statements about multi-way paths rather than about statements of individual rewrites. And then things like Chiara's construction of the proof of the totalitarian principle of quantum mechanics, which says that quantum systems always dominate over classical systems when they interact, should become essentially a statement that the monoidal product of multi-way systems always dominates the Cartesian product of multi-way systems, which I think is that's a statement that we may actually be able to prove very directly, and that's an idea that really came out of our interactions with Chiara. Another community that, I think my final comment would be another community that I think we'd be remiss if we didn't thank is the general kind of graph rewriting, double push-out rewriting, compositional rewriting community. So I at least have had some very nice interactions with the organizers of these Greta seminars, these graph transformation theory and application seminars. They've made us feel incredibly welcome in that community, and within that, I like particularly to isolate Nicolas Baer, who's really been another great source of enthusiasm and energy, and has helped me understand a whole bunch of concepts in graph rewriting that I didn't really understand before, has helped to make these connections to things like tracelets that otherwise I don't think we ever would have encountered, but it turns out tracelets are very directly related to kind of local reasoning about classes of multi-way paths in a way that I think is extremely exciting and that we don't fully understand yet. So Nicholas, I think, deserves special mention, but also Reiko Heckel, who's also been another great source of literature pointers and prompts, and has been a general person that I've been able to kind of submit very naive graph rewriting questions to, and has always been very, very happy to oblige. So we're gradually kind of ticking off these different communities in mathematics and physics, and having extremely productive and pleasant interactions with all of them. And I think it just makes me extremely excited to think about the people that we're going to meet and the ideas that we're likely to encounter as we move into this next year. So I apologize to everyone I've forgotten, but I did think that those people in particular.
Jonathan, numerical relativists.
Oh yes, of course. Yes, no, very good point. Okay, so yes, within the numerical GR community. We've had a bunch. So obviously these ideas are a bit newer. That paper only came out less than 2 months ago, that's had a bit less time to percolate than some of these slightly older ideas. But yeah, particularly within the numerical GR community, well, we've had great interactions with I've had great interactions with people in my home department in Cambridge, and particularly with people like Angaran Thavanesan. Apologies if I slightly butchered your surname there. Who has really been interested in understanding the sort of numerical cosmology aspects of our formalism, understanding what this discretization of the Cauchy problem implies for the boundary conditions of space-time during things like inflationary cosmologies, and how we can go about sort of simulating early universe cosmology using that general approach. Another person within that general community that I think is worth mentioning would be Tiago Franco, who's actually not at Cambridge, he's at Queen Mary, but he comes along to our Cambridge seminars, and he's one of the sort of currently the principal developers of one of the largest scale numerical relativity codes out there, called GR Chombo. Which is it's a relativity sort of module to this general PDE solving framework called Chombo. And Tiago again has been a really interesting person to interact with, and has supplied a lot of really interesting ideas about extension of our kind of hypergraph rewriting techniques to doing kind of more efficient and more general kinds of adaptive mesh refinement for numerical relativity simulations, and has also kind of been a useful source of software engineering assistance and advice to me, at least, in trying to implement kind of more robust and more large-scale simulations of these kinds of numerical relativistic phenomena. I guess more generally, I should thank the entire or particularly the GR Journal Club at my sort of home department in Dampt, Cambridge, for allowing me to sort of present early versions of these ideas and get some really useful and interesting feedback. And again, that's another community, as you say, where we've got very, very nice, energetic feedback, and people seem genuinely interested in what we're doing. Thanks for the reminder.
Well, let's see. Gosh, you're making me. There's a long list of other things. There's all kinds of other people who've been. Jonathan gave a very good list of. I think we have multiple nodes. I'm another node, and there are other connections to me as a node. But I think the main summary is this is both going well as a piece of science, and it's going well as a piece of the structure of science. And it's one of these things where sometimes when one introduces kind of new ideas and a new paradigm in science, everybody says, oh my gosh, this is horrible. That's not happening. Instead, it's, look, it has this connection, that connection. I think it is a challenge, I will admit or say, for people who have learnt a big stack of existing mathematical physics technology. If they want to understand our machine code, that's sometimes challenging because there's just a set of ideas that are getting sort of deeper and deeper that one has to understand. But I think a lot of the interface between existing mathematical physics and what we've done does not need a deep understanding of everything that we've done. And I think it's one of these things where the sooner people start to understand it, the less there will be to understand. If they wait another 3 years, there'll be a lot more that's been figured out, and there's going to be a lot more stuff that it's necessary to understand. I don't think it's going to be one of these cases where I think we are being efficient enough in what we are doing that we are not missing sort of the explanational simplifications that one often gets as fields progress forward. I think it's going to get more sort of deeper and deeper pile of stuff to understand. So that's an ad for, if you're going to get involved sooner rather than later. Because but it also has to say that there are plenty of things where knowing about an existing area of mathematical physics, there's an interface layer that can be operated at which there are super interesting things to be done that don't require you to go all the way down to the details of the machine code. All right, well, let's see. I think we have all kinds of questions and comments here. Maybe we should start taking some of these. So let me take a look at what we've got here. So there was a question from Solar asking, do you have an insight about the existence of supermassive particles and any clue about mu1, G-2 results? Let's dispatch the mu1, G-2 to begin with, okay? So G-2 is this feature of particles like muons and electrons and so on. It's the difference of the gyromagnetic ratio, the magnetic moment divided by spin, to sort of a naive value, and it's a difference that comes about as a result of vacuum fluctuations and quantum field theory. And in a sense, one of the features of G-2, it is the shining example of the success of quantum electrodynamics. It's a place where people use Mathematica, among other things, to do all kinds of elaborate computations where one is putting in a huge amount of work in a model and getting out an answer to, what is it now, 10 decimal digits or something, and then comparing it with experiment and saying it got the right answer. It's a really spectacular piece of sort of theoretical physics. In a sense, what's happening in G-2 is, even though you think you've just got a muon sitting there and it's in a magnetic field and its spin is processing in a certain way, in fact, there are vacuum fluctuations in effect that expose that muon to the effect of, for example, virtual particle-antiparticle pairs associated with all the different possible particles that exist. But as the particles get more massive, the effects of those more massive particles get less important, and so on. And so in a sense, even though you think you have a muon, one of the features of quantum field theory is it's showing you kind of a spectrum of all possible other behaviors. By the way, in our models, that kind of thing sort of shows up in the way that one is using sort of those vacuum fluctuations to create the structure of space in our models. That's kind of the place where that sort of sea of virtual particles lives in our kind of models. But in any case, in the muon G-2 case, one sort of scanning through all of physics and turning that into this one number that is the value of G-2 for the muon, it's a very difficult theoretical calculation. It's also a very difficult experiment. Today, there happens to be some difference between the theoretical results and the experiment. If I were going to be if I were doing stock trading or something, I wouldn't bet on that particular thing surviving. But both sides are very difficult. Whether there's an indication of something fundamentally new going on or not, it's hard to know. I wouldn't bet on it yet. In terms of questions about supermassive particles, an interesting question, because the concept of a particle in our models as a topological obstruction, a localized structure in the hypergraph, there's no guarantee that all sort of persistent structures will have the form of something just like particles. A particle there's a certain sort of fundamental locality to a particle. We don't know that that's the only possibility. We also don't know quite what the analogy is between black holes in space-time and particles in our hypergraph. And it could be the case that, in fact, a particle is just like a very tiny black hole-like thing in this hypergraph. So there may be much more exotic kinds of structures, just like there aren't just black holes, even in general relativity. There are black Saturns and all kinds of other weird types of singularities that can exist even at the level of continuum Einstein equations. So I suspect that they're going to be, there's the possibility of more exotic kinds of structures in our hypergraphs. Now, in terms of supermassive particles, well, interesting question. I mean, as a matter of fact, I worked on many years ago, 1978, I think it was. I wrote a paper with a chap called David Politzer about limits on particle masses in the standard model of particle physics. And it turns out the whole Higgs mechanism stack and so on, which I always thought it was a bit of a hack, but anyway, it is what it is, implies a limit that there can't be things like quarks or leptons that are heavier than, I think, about 200 times the mass of the proton. And so the discovery of the top quark at 173 GeV is an interesting close to saturation of that bound. What happens in that sort of traditional particle physics is the vacuum becomes unstable in certain ways. Now, an interesting question that I have to admit I have not thought about is how does that result from 1978, 1979, how does that play in our current models? How does the instability of the vacuum that's associated, that would happen in the kind of, basically it's a quantum mechanical instability, quantum field theoretic instability of the vacuum that comes about because of virtual fermion loops in affecting the so-called effective potential of the Higgs particle, or the Higgs field. And it's an interesting question how that would work in our models, and I don't know the answer, and what it would mean for the instability, because one of the things that wasn't clear there is, okay, so the universe becomes unstable, so what? So what actually happens? Good question, I don't know the answer. I mean, in our models, one of the indications is that there might be particles much lighter than the electron, for example, because in our models with our sort of estimates for the size of the elementary length, an electron might consist of, it might be very small, like 10 to the minus 80 meters across, where the size of a proton is like 10 to the minus 15 meters. So it's very, very tiny compared to the size of a proton. The best bounds we have on the size of an electron right now is that it's smaller than about 10 to the minus 21 meters. So 10 to the minus 80 meters is really, really tiny compared to that. But anyway, that's kind of an indication of that. But the electron still at that scale size is still around 10 to the 30th elementary elements of the hypergraph. And so that allows the possibility of much lighter particles that could exist in the universe, and perhaps 10 to the minus 20 electron volts, which is kind of around the bound for the lightest particles that can make up the dark matter in the universe. So we're curious about whether there's a connection between this kind of, the possibility, we don't know it exists, of these kind of oligon particles, the few hypergraph edges particles in our models, and the kind of thing that could make dark matter in the universe. Okay, comment from Ambitious. rough ETAs for the development of the blockchain idea, the blockchain project can help fund the project as a whole. Yeah, it's a funny thing. I mean, it's like you can do projects that make money, or you can do projects that create the structure of money, in a sense. The blockchain projects are of the second kind. We're working on it. We're not sure how it's going to work out. It's still, there's both the idea part of it, which is actually in pretty good shape, and first implementation exists. The deployment and how to actually deploy it, we've been pretty involved in the blockchain world. Wolfram language is connected to many blockchains. We've done a bunch of things there. The practical deployment is a complicated thing, and we're not quite sure how that's going to work, and we're not quite sure to what extent we're just going to put the ideas out there for other people to implement, and to what extent we're going to deliver a practical implementation that can actually be used as a transaction network and so on. And there are also things where it's kind of funny. The issues that we have are the exact same issues that we have in understanding quantum mechanics. So it's not like we get to do blockchain and then we get, the next day we get to do quantum mechanics. It's like, it's the same problem. So that's what's happening there. But I'm hoping within the next month or two, we'll have some good things to say about that. Boy, there's a question about specific work here. The challenge is always when you ask about specific work that somebody is doing, it's always very difficult to understand it takes real effort to understand what people have done. I'm scanning through this, but I can't tell you quickly. Wow, that's interesting. That's I think I know more or less the tradition this is coming from, but I don't know any details. I can't really be helpful there. It's a question from Itamar. Can you elaborate regarding consciousness? Have you noticed anything odd we could investigate with our eyes closed or open, so to speak? I wrote a piece about consciousness. You can find it on my writings. It's also linked from the physics project website, wolframphysics.org. Wrote a piece recently about consciousness. I gave a talk, which I'm sure you can also find like a week or so ago, to a group of philosophers about the consciousness problem. So that's a little bit more detail about it. In terms of how to think about sort of the experimental sort of consequences of a theory of consciousness, I'm not sure I really have those, other than these statements about the difficulties of understanding distributed computing and the way that maps into sort of this understanding of how consciousness generates laws of physics. But I would encourage you to look at the piece that I wrote and maybe the talk that I gave to philosophers. When was it? Last week, I think. Okay, so question from John: what is entanglement in Wolfram Physics Project terms? I think I should let Jonathan answer a question here. I'm happy to try and do this one, but Jonathan, this is why don't do you want to take this one?
Yeah, sure. I mean, it's actually quite a deep. I mean, it doesn't sound like it, but it's actually quite a deep question, because it relates to essentially this problem of what is it that distinguishes, well, multi-way systems from non-multi-way systems and quantum mechanics from classical physics. Because the important feature about multi-way evolution graphs that Stephen, I think, alluded to, but it's worth kind of restating, is that in addition to the thing just branching, things can also merge, right? Because states obtained on different parts of the multi-way system can become isomorphic as hypergraphs or whatever they happen to be. Post bifurcation, two multi-way paths can actually merge. Now, one of the implications of that is that when we compose multi-way systems together in parallel, when we take a sort of tensor product of them, or what in category theory we would call a monoidal product of them, and we do this by, say, taking a disjoint union of subrelations for our rules, what you get is not a straightforward, if your multi-way systems just branched, if they were just pure trees, and you took a tensor product of those, it would be just an ordinary Cartesian product. You just get a bigger tree. The fact that they're not trees, the fact that the states have isomorphism checking, that there's a non-trivial equivalence function, means that when you take that product, the things can merge together. And so you're taking a product, but where there's a non-trivial, what you might call a gluing function. So that's something that kind of merges the branches on the two sides of the product, which means that unlike with a Cartesian product, you cannot neatly, once you've taken that product, you can't neatly separate it out into the two constituent multiway systems. So in other words, the subsystems that you producted together are non-separable subsystems. Whereas if you've just taken a Cartesian product, by just sticking two trees together with a common root, you could separate them. And that's deeply related to this idea in the foundations of QM, where the thing that essentially distinguishes quantum mechanics from classical mechanics is the non-separability of subsystems. So in classical mechanics, if I have two classical systems and I put them together, I can always separate them out again back into two classical systems. In quantum mechanics, I can't do that. If I have two quantum systems and I let them become entangled, what it means for them to be entangled is they're no longer separable into isolatable subsystems, and that relates to these problems about the issue of measurement that Stephen was alluding to earlier, because effectively measurement occurs when you as an observer become entangled with the system you're observing, so that this view that you as an observer are separated from the system you're observing becomes false, because the two of you form now a single non-separable subsystem. All of which is to say that this crucial non-separability idea of QM is formalized in terms of the gluing transformation on multiway paths. And so concretely, the way we can see that is by looking at a branch yield graph. So when we take a multiway evolution graph and we slice it horizontally, we can look at the branch yield graph, which is telling us the ancestry distance, or at least it's giving us at least an approximation to the ancestry distance between the states. So again, if that multiway graph were just a tree, that branch yield graph would be a totally trivial, disconnected, a totally disconnected thing. The fact that there's merging and that therefore you have non-separability is why you get these non-trivial branch yield edges. And it's why we say those branch yield edges are giving us a quote unquote map of entanglement, because they're telling us which subsystems in the multiway evolution graph are and are not separable. And if they're connected by a branch yield edge, it means they're not separable, and therefore that they are entangled. So at a trivial level, entanglement is just given by the combinatorial structure of the branch yield graph. But John's question actually gets towards this much deeper question of what is it that really distinguishes classical physics from quantum mechanics? That's an initial answer.
Sounded good to me. It's although I'm not sure that we should be answering in terms of disjoint unions of things in categories or not. This is always very hard to know in these discussions how deeply technical we can get. All right, there was a question from T-Bod here. What is the theory predicted correctly that wasn't known before, or is that forthcoming? We don't yet have something where we can say it's a fantastic sort of party trick for theories to be able to say this is the thing that we predict that nobody knew before, that you can go out and measure and find out is correct. It's super difficult to do that from a theory as deep as this one. Not in terms of having new things to say about the world, but in terms of connecting those new things that one has to say about the world to practical experiments that can be done with current equipment and so on. I mean, we have plenty of new things to say if you could only probe the world at a length scale of 10 to the minus 100 meters or something, but we can't. So we have to find ways to sort of build up to something that we can see in the current world. The most impressive things right now, I think, have to do with the very detailed practical reproduction of things that were already predicted by other theories. We can now predict in a cleaner, stronger, more principled way than was possible before. And we've got these indications of new things that one might see, but we don't know quite the scale on which you'll see them. But there may also be some scale independent predictions, but there's just a lot of physics work to be done in figuring those out. And it's an interesting question whether the first kind of really clear sort of experimental implications of our models will happen at the cosmological scale in astrophysics or astrophysical scale, whether they'll happen at the microscopic particle physics, quantum mechanics scale. I'm not sure. There are different things in different places, and each one is a possibility. I'm kind of hoping over the next year that we'll start seeing some actual experiments start to get done, looking for some of these kinds of effects in our models. I think there have been a lot of experimental physicists who've been interested in doing those things. and they say, what should we look for? And it's like, we're not quite ready yet. We can't tell you exactly what to look for, but we should be getting ready. And we're certainly right now, one of my projects is trying to look more at the phenomenology of our models and trying to see in a more practical way kind of what actual specific predictions we can make, even if we don't know the precise scale at which these predictions happen. There's a question from Lurch. Isn't entanglement what creates space and gravity? That's becoming a popular idea in mathematical physics and in our models. You could say that in some sense. I mean, in our models, we have a very concrete picture of how space is created, not time, how space is created. And we also have a concrete picture of how time is created, but that's a little different. But yes, the kind of formation of space happens as a result of this kind of the evolution of this hypergraph. The evolution of the hypergraph inevitably involves this multi-way graph, which involves entanglement. And it's an interesting question, to what extent you could have a non-entangled, that is a single-way system that still has hypergraph evolution that can knit a structure of space without having all these entangled possibilities. Jonathan, have you thought about that? Do you know the answer to that?
Yes, but I also have a broader answer to this question, if that's useful.
Go ahead. But actually, I want to know your answer. I want to know your answer to the thing I just posed, but then you can answer the broader question.
Right. Well, so in terms of the context, so if you take what I just said, which is sort of in a sense, if you just had a sort of a classical physics system where you just had a sort of tree-like multi-way evolution graph, clearly there's no merging, there's no sort of entanglement structure. Every subsystem is separable. Well, now imagine you repeated the same picture, but in a space-time causal graph, just for a single path. So now, so you have a purely tree-like causal graph. What that's telling you effectively is that your Wolfram model rule, your hypergraph rule, is simulable with a neighborhood independent substitution system, because it's telling you that there's no causal interaction between neighboring points in space. So in effect, what you have is a universe, but where the spatial structure is kind of trivial because it's just neighborhood independent. And so the fact that you don't have a tree, just like the fact that you don't have a tree-like multi-way evolution graph is crucial for you having quantum entanglement. The fact that, and therefore a non-trivial quantum structure, the fact that you don't have a tree-like causal graph is responsible for the fact that you actually have a non-trivial geometry of space and therefore of space-time. And but both of these are in a sense approximations, right? The multi-way evolution graph and the causal graph are two types of approximation to this more general structure, which is the multi-way causal graph or the multi-way evolution causal graph, depending on how you want to think about it. And actually, as we were discussing in the live stream yesterday, one of the important features of the multi-way causal graph is that there is ambiguity about what is spatially separated and what is branchially separated, what is separated in the space-time causal graph and what is separated in the multi-way evolution causal graph, because both types of separation just manifest as sort of anti-chain, non-causally related sets of points in that multi-way causal graph. And one of the implications of that is that there's ambiguity, therefore, in whether you project that onto a space-like hypersurface, or you project it onto a branch-like hypersurface, or something in between, which is kind of what we think is related to the holographic principle and to ADS-CFT correspondence and things like that. And so one of the implications of that is that the cohesive structure of space and space-time and the non-trivial quantum entanglement structure of your projective Hilbert space are coming effectively from the same source. They're coming from the fact that the multi-way causal graph is a combinatorially non-trivial structure. And the fact is, you can project in one direction, you can project to get the entanglement structure. In another direction, you can project to get the spatial structure. And that gives you a much more direct, and in my view, much cleaner way of thinking about this emergent space-time from quantum entanglement idea that, as you correctly say, Stephen, has been kind of a major feature of recent fundamental physics. Things like the general it from qubit program and the idea that somehow entanglement metrics may be able to give you something that limits to a space-time metric. This is a very, very clean way of seeing how that might actually work by taking these different projections. And one of the corollaries of that is, to answer, in relation to your second question, that anytime you have a system that, unless you enforce some ridiculously sort of rigid gauge constraints, anytime you have a system that's going to give you a cohesive spatial structure, it will also give you a cohesive sort of entanglement space or branchial space structure, because essentially your multi-way causal graph is equally rich, independent of which direction you project it in. That's a slightly hand-wavy statement. There are ways you can make that more formal, but that's the basic idea.
Well, so the claim is, if you are spatially non-trivial, you are also branchially non-trivial. That's the claim, basically.
Right. So if your system were a neighborhood independent substitution system, then the causal graph
is more subtle than that, because combinators, for example, which are branchially non-trivial, but spatially don't really have an extent, but they have this weird tree-like version of space. Different conversation.
Right, but okay, this is a different topic, but I personally have never really understood why we have this notion of tree-like separation. It seems that tree-like separation is just space-like separation, but where effectively there's a distinguished origin point, which is the root vertex. But
okay, separate. Let's not go down that path. This is about to. You might be right, but okay. Let's see. We've got some other comments and questions here. Okay, there's a question from Chattertan. Since all possible rules are running in rulal space, is there a rule that generates a branch with magic, with Star Trek physics, etc.? Can you transfer from one rule branch to another? Very interesting question, right? So how do you move from one rulal reference frame to another? The answer is you change your description of physics. And what's involved in changing your description of physics? Well, we believe that all of physics is ultimately computational. So in a sense, what you're doing is you're saying, in one description of physics, you're running a simulation of another description of physics. So if you want the Star Trek universe, then you can get that in our universe by running a simulation of the Star Trek universe. Although that simulation necessarily will run slower, even if we had the most optimized computer in our universe, simulating that alternative universe will run slower. And that's kind of a statement of saying that as you, that's a, how to think about that. I mean, I think that's sort of related to time dilation in rulal space, that you end up with something where you have a, so the question is, as you are going to, choose this other path in rulal space, how fast can you get there? And the answer is that there is a parameter in rulal space, which is the analog of the speed of light in physical space, the maximum entanglement speed in branchial space. There is a maximum rulal speed, we've been calling it rho, and the maximum rulal speed is, and this is a very bizarre kind of concept, it is the ultimate processing speed of the universe. It is, what units is it in? My favorite version of the units for it, you can pick, like you can pick for the speed of light, you can pick either meters per second, or you could pick, kiloparsecs per year or something. You can, as the units. So in the maximum rulal speed, one set of units you can pick, it's the processing speed of the universe. So my favorite speed to pick, my favorite units will be Wolfram language tokens per second. It's if you are processing a piece of Wolfram language code, if the universe is running a piece of Wolfram language code, how fast can it run it? So if you were to compile it into the underlying rules of the universe, how fast would it run? And one vague estimate I have is about 10 to the 450 Wolfram language tokens per second. So that essentially gives you, if you were to make the most optimal translation from one rulal reference frame to another, that gives you kind of the parameter analogous to the speed of light for making that translation. So I think the answer is we can simulate in our universe with computation, we can simulate other sort of points of view, but for us to fundamentally live those points of view, we have to be interpreting the universe in a different way from the way we're interpreting the universe. If we were to not pick our description of space as we pick it, but in a different way, we would end up with different effective laws of physics. We could end up with effective laws of physics that look like magic with respect to our current way of understanding the universe. Now, this is closely related, I think, to a question, when you think about extraterrestrial intelligence, for example, and you say, there's a pulsar magnetosphere that's generating this weird sequence of radio signals. Is it intelligent, so to speak? Is the weather, does the weather really have a mind of its own, and so on? In a sense, what's happening is those things are at different places in Rullial space. And the question is, what's involved in making a translation between our way of thinking about things and theirs? And how difficult is that? What's the metric of distance in Rullial space? Not stuff we understand yet terribly well. I think that the way to think about it is we live in a certain place in physical space. We also live in a certain place in Rullial space because of the way that we choose to parse to understand the universe. And the universe is actually a lot bigger than we thought it was. We can both move around in physical space, and we can, in principle, move around in Rullial space, although the whole development of our civilization and our biology and our science is based on a particular reference frame in Rullial space, and it's not trivial to get to another one. But in a sense, that's kind of there's a bigger universe out there because there are many points of view about how the universe works that are completely alien to us, that we've not been able to take. There's this giant sort of Rullial universe of possibilities, in addition to the giant physical universe of actual places where you can visit in a spacecraft, so to speak. So in a sense, I think the best way to talk about, and I need to understand this better, to think about sort of motion in Rullial space has to do with sort of simulation of different possible rules for the universe. I mean, I think the thing to say is that in some sense, the most fundamental thing we're discovering in our model of physics is that the universe is computational, that it really is the case that you could use a Turing machine or all kinds of other things, and you can simulate our universe. That's not obvious. That seems to be a fundamental law of physics. In fact, one might even argue the fundamental law of physics, from which you can derive essentially everything else. But good question, which we don't understand as well as we should, and I'm hoping to explore that some more. And my efforts in why does the universe exist relate closely to these kinds of questions. Okay, question from Senri about, seems like there's connection to AI that can be made with the things we've done about automated theorem proving. Any comments on this? Okay, there's one type of comment which has to do with understanding machine learning in terms of multiway graphs, which is rather embryonic, and we haven't really figured that out. There's another much more concrete thing, which is in automated theorem proving, the story is, can you find a path through the multiway graph? And Jonathan in particular has a new approach to that. That's the real question is, there are many steps, there are many different possibilities you can choose to find that path. What's the best way to find the path? What are the best lemmas, for example, to try using to best find the path? And one can try to use machine learning to guess what are the best lemmas to use, but Jonathan has a more principled approach that is based on using essentially causal information in the multiway graph to get an idea what lemmas should be used. My version of Jonathan's thing, which doesn't sound very good, but it's not as uncomplimentary as it sounds, is Jonathan's approach is use the lemmas that are most useful. Use the lemmas that are used the most. But basically, it's a principled way of speeding up automated theorem proving that, like so many examples in machine learning and so on, in the end, there's probably an algorithm that does better than the sort of flapping around in neural network space, so to speak. But if you don't know any better, flapping around in neural network space does pretty well. But this may be an actual principled algorithm for doing theorem proving more efficiently. Jonathan, do you want to comment on that?
Yeah, no, I think that is a pretty good summary. I mean, the basic problem with automated theorem proving is you have deductive inference rules. You have what is called a proof calculus or refutation complete calculus, which just tells you how you can form lemmas, how you can form substitution lemmas that take you along a multi-way path, or critical pair lemmas that merge multi-way paths. But those inference rules don't really tell you if you have a class of lemmas that can be applied, which ones actually to apply. And the conventional way of doing that, of making that decision in ordinary automated theorem proving algorithms, is to use the standard ordering on the terms that appear in the proof calculus, which is this what's called the reduction ordering. Now, just because that's a sort of natural ordering to use doesn't mean that it's optimal. In fact, we know in most cases it's not. And kind of the idea that's come out of thinking of multi-way systems as more than just abstract rewriting systems. They are abstract, what a multi-way system really is, in my view, is some kind of hybrid between an abstract rewriting system and a causal set, because it's an abstract rewriting system that is enriched with additional causal structure. And so because of that, we can introduce a new ordering on the terms that goes beyond what people just do in the pure abstract rewriting case, which is to select lemmas associated with paths that have the highest causal edge density. And so as Stephen said, effectively what that's doing is it's saying pick the lemmas that are the most useful, where in our case, in our situation, useful just means that they have the greatest causal influence on future paths. And if they have more causal influence, we can use that as an approximate heuristic for assuming that they're going to have the greatest effect on shortening future proofs of lemmas and propositions and things. Okay, in the second ZX paper that we put out just over a week ago now, this is again joint work with myself, Mano, and Xerxes. We applied this to a particular class of examples for diagrammatic reasoning in quantum information theory for proving statements about quantum circuits, because the causal structure of something like a ZX diagram in quantum mechanics is very, very well defined. But we're very excited, and I'm particularly excited on seeing how we can apply that to other kinds of rewriting calculi, other kinds of theorem proving contexts, as well as a more general kind of, beyond physics, pure mathematical logic implication of the project. Another thing, okay, I'm not going to say too much about machine learning because I don't really know anything about it. But one thing that I think does seem potentially worth investigating is using a kind of causally enriched approach to doing something like gradient descent. If you're in some parameter space, you're searching for some minimum somewhere. You can think about that search as being a kind of as being some continuum analog of a multi-way system sort of path enumeration search. And if there's a way of finding minima by using causal information that is not just there in the abstract rewriting structure, I suspect there may be a new kind of first order numerical method that lets you go beyond what you could do with kind of naive gradient descent methods. But that's something that needs to be.
There's a general class of things which we're just starting to explore, which is carrying causal information in programs. Programs usually, you run a program as a function f, a function g, you evaluate f, you evaluate g, you get results. What that is not capturing is the causal information of what aspect of the input to f and g affected what aspect of the output. Carrying that causal information, which by the way is not completely unrelated to automatic differentiation and things in machine learning, is something interesting, and I've been thinking about language design around those kinds of ideas. Jonathan, you didn't mention something that I thought was interesting that you were starting to look at, which is the application of automated theorem proving on proofs in automated theorem proving. That is, as given a proof in automated theorem proving, it's not clear that that proof that you find by this automated theorem proving process is in any way optimal. There may be many different proofs of the same theorem. And so the question is, can you use these methods to basically take one proof path and evolve it to another proof path? So for example, I think Jonathan just developed some set of rules for evolving proof paths, and I want to apply it to the automated proof that I got 20 years ago of the simplest axiom system for Boolean algebra, which is this immensely complicated proof that no human has ever understood. And I would really like to see whether we can get a simpler version of that proof, which probably still no human will understand, but maybe instead of 100 lemmas, it'll have 50 lemmas, which makes it, that makes it easier or harder to understand. But I think it's an interesting, this notion of proof-to-proof transformations, which is very related to this higher category theory business and to homotopy type theory, this is another frontier of what we're doing, is the path-to-path transformations, proof-to-proof transformations, and so on. Something which has not been well thought about that we can see in either general relativity or quantum mechanics. The sort of the path-to-path transformation story.
It's kind of it's like a perturbation theory on multi-way evolution paths, which, as you say, is directly relates. I'm just going to give a call out to some of the work that Xerxes and I are currently doing relating to homotopy type theory. This is kind of a very concrete diagrammatic way of thinking about that whole construction.
Let's see. Wave is asking, care to explain the thinking that string rewriting would somehow be isomorphic with string theory's strings? Yeah, this was a kind of a pun of mine from a year ago that I'm very frustrated. No string theorists have, it seems like every string theorist who gets involved with our project decides that they're just going to work on our project and not going to work on string theory, but what I think is going to be really fertile is making the connection between our project and string theory. The question is, can we represent kind of string field theory particularly, which has this seems to have this kind of multi-way character? Can we think about that as a limit of rewritings of character strings? And I still think the answer is yes, but nobody has figured it out yet, to my knowledge. Jonathan, do you know anybody who's actually worked seriously on that? I think we haven't been able to. Maybe somebody's working on it and they're about to write the great paper, which is going to show that this is true or not true. I bet it's true. But we'll see how it plays out. Jonathan, any comments on this?
So I'm not aware of anyone who's about to make a revolution. We had a winter school project that was focusing on this, that made good progress, at least to formalizing notions like normal ordering in quantum field theory in the context of string rewriting systems, which I think is a good first step towards this project. But yes, I think the direction, Stephen, that you've proposed, which is essentially take an n character string substitution system and treat each n character a string substitution system with an n character alphabet, and treat each one of the characters in that string as being essentially a specification of one of n directions in which to in which to perturb some extended one-dimensional object, and then just look at the world sheet that's produced by that object and see if you can derive an action principle on it. That's something which, partly as a consequence of some of the numerical relativity work, we should now have a way of we should actually have the technology to be able to address that question, because we're starting to get, good functionality for translating between a sort of Cauchy development of an initial state and some associated action principle. And if we can do that and show that there's a class that, that limits to the Polyakov action or the Nambu-Goto action or whatever, some well-known, well-defined action in string field theory, then I think we can say that pun has actually become science. But I think there are a few things that have to be developed before we get to that point.
Let's see. Okay, let's see, Jamie here. Who can most benefit immediately from using the current model of the universe? Well, I mean, as we mentioned, there are these very practical areas of, doing numerical relativity, calculating mergers of black holes and things, doing circuit optimization in quantum information theory. These are very immediate, concrete places where the formalism we've developed can be used. These applications outside of fundamental physics also have potential near-term consequences. I would say if we can get a calculational method for quantum field theory, that's a big deal for actually doing physics. I mean, there are lots of questions about QCD and so on that are potentially accessible. If we can get a much more effective way of doing practical quantum field theory computations that can include scattering and all kinds of things like this that have not traditionally been able to be addressed by sort of numerical quantum field theory, because lattice gauge theory tends to use a setup where time is really very much the same kind of thing as space. And so you can't have things like propagation of particles. You can't have things like ordinary scattering. So that would be a very good use in quantum field theory. Let's see, a question from Kine. Can you elaborate on why we use category theory? Well, I was afraid of category theory until about a year ago. And then I started realizing that category theory is an infrastructural theory in the following sense. It is in the same sense that if I think about kind of the computational language we have in Wolfram language, the infrastructure of that is the idea that everything is a symbolic expression and that things progress by transformations between symbolic expressions. That's kind of an infrastructural way of thinking about things. Whatever you have, if it's a document, a plot, a mathematical expression, it's all represented as a symbolic expression, and everything you do to the symbolic expression can be represented in terms of transformation rules for patterns of symbolic expressions. That's an infrastructural way of thinking about computation. That's proved to be very valuable and a very good match in that particular case between the way us humans think about things and the way computers can do things. So category theory is an attempt to be the same kind of infrastructural system for representing, in a sense, the structure of mathematical reasoning. And in some sense, it's you could say it's kind of like, it's a little bit maybe like the object-oriented programming of mathematics, so to speak, and it even has objects in it in categories, that it's kind of a management system for dealing with constructs in mathematics. And normally the way category theory is used is they're just, it's some category and it has these different kinds of objects and there are a small number of them and each of them has a name and so on, very much like the way symbolic expressions are used in Wolfram language. Each piece of a symbolic expression has a name, has a meaning we know, et cetera, et cetera, et cetera. What's happened in the physics project is actually the idea of symbolic expressions, which, and let's talk about those first. We're using what amount to symbolic expressions, but they are anonymous. We don't care. It's like we could name every atom of space. We could say, this is the blue atom of space. This is the atom of space that has coordinates such and such. This is the atom of space that has this feature. This is the atom of space that lives on the edge of the black hole. This is et cetera, et cetera, et cetera. But we're not doing that. We're just saying they're all just elements. They're all abstract elements. They're all abstract atoms of space. But we still have the same structure of essentially transformations of relations between these elements. That structure is like transformation rules between symbolic expressions, but it no longer has the meaning that we normally attach to it. It's a pure infrastructure use of symbolic expressions and transformation rules. Similarly, in category theory, the most usual use of it is at the level of being able to talk about sort of particular objects with particular names and give them particular labels and so on. We're using it at a more infrastructural level. We're using it at a more bulk level where we have these objects, these sort of giant sequences of morphisms and so on that represent actual sort of progress through time of multiway graphs and things like that. So we're using sort of the infrastructure of category theory, and we're using the structural ideas of category theory, but we're not using the name these objects, name these particular things version of category theory. And so, but nevertheless, there are sort of generalized notions of how structures connect that have emerged in category theory, and those are what we're making use of. Jonathan, do you want to give another version of this?
Yeah, sure. I mean, I think that's a pretty good summary. So my philosophical sort of perspective on category theory, I'm not claiming it's original, but it's the one that I sort of stick by is, category is one approach to doing, this thing that you, Stephen, were talking about earlier on of this trying to develop a theory of meta-mathematics in bulk. It's operating at a slightly different level. Most of mathematics is about talking about specific mathematical structures like specific groups or rings or fields or topological spaces or whatever. Category theory is based on this observation that if you look at the class of all mathematical objects of a particular type, or a particular kind, I should say, not type in the formal sense, then that class itself forms a mathematical object with some non-trivial properties. And that's what a category is trying to formalize. So instead of thinking about a particular group, you would think about the category of groups in which each object is a group and each morphism is a group homomorphism. Or you think about the category of vector spaces in which each object is a vector space and each morphism is a linear transformation, or in the finite dimensional case, each morphism is a matrix or something. And then there are these operations that you can do, like reversing the direction of the arrows, which sort of generalizes reversing a group homomorphism or taking the Hermitian adjoint of a linear operator or whatever, and you can define functorial transformations between these categories that tell you essentially how these different fields of mathematics relate to each other at a very bulk level, like this idea of what is it when we talk about group representation theory? What is it that we're really doing? Well, what we're really doing is we're defining a functorial transformation from a category of groups to a category of vector spaces that is faithful in the sense that it preserves some structure. So we're mapping particular elements of groups onto particular linear transformations of finite dimensional vector spaces. And so we're mapping parts of one category onto essentially morphisms of another category. So in that sense, as Stephen said, it's category theory is a very kind of infrastructural, very bureaucratic sort of meta theory of mathematical structure. In effect, one way you can think about this, the Wolfram model and the Wolfram physics project is a very infrastructural, bureaucratic way of thinking about fundamental physics, which as a nice corollary seems to encapsulate also metamathematics as a kind of, as a side project, so to speak. That, in a sense, the Wolfram model is not in itself a theory of physics. What it is a very general abstract infrastructural formalism for encoding theories of physics and seeing how they relate to one another, much like much like the formalism of category theory. And perhaps unsurprisingly, therefore, there is a very direct translation of, the sequential composition of arrows in a multi-way evolution graph gives us effectively the composition of morphisms in some category, or the parallel evolution of two multi-way threads gives us essentially a monoidal composition of morphisms. And, a completion operation between two paths effectively defines a higher order morphism, a k morphism between k-1 morphisms, from which we can then construct higher categories and so on. So there's a very, very natural mapping from our multi-way system formalism to the category theory formalism, which I think is really illustrating that what we're doing is going beyond a theory of metamathematics in bulk, which is what category theory is intended to be, to being a theory of both, of at least fundamental physics and metamathematics, and probably lots of other things as well in bulk, which necessarily means that category theory is a kind of limiting case. That would be the, and so, sorry.
Yeah, one thing I was just going to add to that is that the thing to realize is that, in a sense, 20th century physics is also just bureaucracy, in the same sense as you're saying, category theory and our fundamental formalism is sort of just bureaucracy. It turns out that, general relativity is, in a sense, just bureaucracy relative to, it is a purely sort of, in some sense, bureaucratic result of the bulk effect of these atoms of space and so on. It's something that doesn't depend on the precise details of the rule. It depends only on the structural setup, the bureaucracy of the situation. I mean, that's one of the surprising things, and one of the things which is that things like relativity and quantum mechanics are robust and generic, which was not obvious to me, at least. That would be the case, that they would be generic features of classes of models. And the fact is that the categorical level is probably capturing that same thing that is generic, so to speak.
I agree. And just one final thing to add on that. I mean, just at a practical level, one reason why we're interested in category theory in the context of the project is because it has had a long and fairly distinguished history of essentially developing ways of thinking about how processes compose. I mean, at some level, that's a way that you can think about what category theory is about. You have morphisms, which are some general way of representing processes, be they, as I say, linear transformations between vector spaces, or, processes in quantum mechanics or whatever, and understanding how they compose in sequence or in parallel, or how they have, higher order morphisms between processes, or how you can define functors that map, collections of processes to other collections of processes and invert some arrows and don't invert other arrows and so on. And there's been this whole rich formalism developed in category theory and higher order category theory for understanding generally how processes in mathematics and in physics compose. And in effect, that formalism is useful as a starting point for our multi-way evolution graphs, which are kind of taking those ideas and trying to extend them even further and give a kind of explicitly constructivist context within which we can understand these compositional ideas. And so we make extensive use of the compositional ideas that come from category theory, but also as a kind of as a nice feedback, our multi-way evolution graphs give us a new and more explicitly constructivist perspective on how those compositional ideas really arise and what they really mean at some deeper level.
I mean, the two probably short-term coming attractions for category theory from what we've done. One is computationally bounded category theory, where the morphisms aren't just free, but have some computational costs associated with them. And the other is causal graphs meets category theory, which I think is another place where we're going to be able to contribute to the category theory story. Let's see, William comments about the nature of time and the perception of, for example, musical notes, that we experience a flow of time. Yeah, I mean, a lot of what we humans do is deeply sequentialized. For example, human language is a sequential thing. And as a designer of computational language, I have long been interested in, is that the only thing we can do? Does it always have to be somehow sequentialized in the way that it's presented? Could we have a picture language that works as well? Could we have something that's based on graphs that works as well? The thing that I've found over the last 40 years of trying to do this is we humans are pretty good at understanding the sequentialized stuff. We're pretty confused when it comes to other kinds of things. At least most of us are. I am, for example. I think that, so there is something about whether it's language, music, whatever, there's a certain sequentialization that we're used to. Time is very important to us. It is the flow of things in time is something that is very characteristic of our experience of the universe. You know, I worked on this science fiction movie called Arrival, which is one of the better attempts to kind of have a view of kind of what it might be like to be a critter that doesn't have the view of time that we have, the sequentialized view of time. The critters that happen to be 7-feeted heptapods in that movie have a view of time in which time comes in one lump. You don't think about the progression of time, you just think about the what will happen. It's like the principle of least action in physics is just says the path of the particle will be the one that minimizes the action. It doesn't say the path of the particle will be sequentially constructed by an equation of motion going along. And so it's an attempt to kind of, that movie is an attempt to, and then the short story that it came from by Ted Chiang was an attempt to kind of conceptualize what it means to exist in a way where time is not sequentialized. I haven't watched that movie actually since it came out several years ago now, but and I certainly haven't watched it since I've thought about the physics project. I did realize that some of the things that we did for that movie actually have in some bizarre way informed this physics project, and even but that's an attempt. You know, I view it as being a very interesting challenge for science fiction writers. In fact, a couple ones who I communicate with them at my consciousness post may even be working on this now. It's an interesting challenge for science fiction writers to try and write about what is it like to have a different experience of time? What is it like to experience the universe not as a sequentialized consciousness, so to speak? And, you know, maybe it's maybe one of these cases where you could write a terrific story, but no human will ever understand it. Which is kind of like you can have a different real reference frame, but we just can't get there. Or there may be a bridge between them, which one will be able to get. It's sort of a science fiction exercise in science, so to speak, I think, to do that. Let's see. Russell is asking, can you explain why it is possible to construct algebras that allow us to have reduction systems in the context of emergent structure? So maybe the question here is, why is there computational reducibility in a computational system? Yeah, I mean, you can think about it in terms of computational complexity theory and speed up theorems in computation theory and so on. I don't think, there's probably more that we can do to really explain what is the spectrum of computational reducibilities in a computational system. I looked at a little bit in chapter 10 of my New Kind of Science book, which is about processes of perception and analysis. And I looked a little bit at this question of what are all possible computational reductions that you can make of something. I didn't get that far with it. It's kind of like asking what are all possible statistical tests you can apply to things. And pretty quickly you end up getting into this kind of the model independent model trap of saying, I'm going to have this thing, it's a neural net, it can represent anything. Well, it represents anything, but it represents it within a particular framework. And it's difficult to break out of that. But an interesting question. Okay, it's a question from Alistair about particles. That's our homework for the next few months, is finding particles. We haven't done it yet. Dan is asking favorite findings thanks to Wolfram Physics Project. I mean, look, the favorite meta finding is this is a much more beautiful universe than I ever imagined. I mean, just the the extent to which abstraction and very high levels of abstraction directly play into the story of how our universe works is to me truly remarkable, and something that is a piece of sort of abstract aesthetics far beyond what I thought existed. And certainly as we think about this kind of rulal space and the relationship between the formal and the actualizable in the universe, these are just, to me, sort of an amazing sort of convergence of the formal and the actual, so to speak, in a way that I didn't see coming particularly. Okay, let's see. Russell is asking, have you considered making every irreducible thing an atomic type? Is it important to have a type system for this that's like word embeddings? So the point about just saying, forget the irreducibility, let's just crush it into one thing, is that will not lead to, if you do that, you will not be able to disentangle what a computationally bounded observer would perceive. You will just basically crush everything to nothing. And it's like saying, and you will not have kind of, you'll not be able to understand the consistency conditions between different kinds of processes that happen in the world, so to speak. So I think it's like, that will be a typical thing that you would do in sort of a non-computationally informed approach to mathematics, or to category theory for that matter, is just to say, it's a morphism, boom, it happens. But the question is, what is the process by which it happens? What is the, how do we think about that in terms of the machine code? What is the low-level computational process that makes it happen? And as we start to understand that, we start to be more realistic about what's going on, and we start to be able to inject what a computationally bounded observer can perceive about the thing that's happening there. Jonathan, do you have a different version of that?
On that particular question, yeah, sure. I mean, that's what lemma formation
is crushing things. Yes, but the issue is, if you lemma form everything, you end up with nothing. I mean, you have no structure anymore.
Isn't that what you just said?
Yes, I think it is.
Yeah, okay, yes.
Anders asks, can our model explain strong emergence? I don't know what you mean by strong emergence, I have to say. I mean, the whole story of simple computational rules lead to elaborately complex behavior. That's the kind of story of the principle of computational equivalence, of computational irreducibility, and so on. Some people, I think about the emergence as being something emerges from some underlying rules where it wasn't obvious what you put, what you get out was ever put in. That's kind of the whole story of our models, is the most extreme form of emergence one can imagine, which is from essentially nothing and the most simple, most generic rules you can imagine, generating everything in our universe, seems like the biggest span of emergence that you can imagine. And that's what we're dealing with here. So whether that counts as strong emergence, I don't know, but that's a pretty big span of emergence, I think, that needs to happen there. Should probably wrap up soon here, but let's see, question from Axel Landrian. How particles like electrons look according to this project? How many nodes are needed to describe a particle like an electron? Yeah, well, good question. We don't yet know the answer to that. Particles are some kind of topological obstructions in our network. They are sort of somehow stable with respect to the rewriting processes in the network things. We think we may be able to get a handle on them using ideas like homotopy, and in much the same way that you can classify like vortices in a fluid in terms of homotopy, or other kinds of topological defects in materials and things in terms of homotopy. A generalization of that is what we're hoping will allow us to understand how particles work. That sort of discreteness of these homotopy groups and so on is probably going to be related to the quantization of things like spin and quantum numbers in particle physics, but we don't yet know exactly how that works. That's really an important thing for the next few months to be able to try to resolve that. Okay, Jonathan's saying we have solitons. Comments. What were you?
No, that was from several questions ago. It's not worth. I mean, yes, we have a way of computing discrete homotopy groups, and we have models of topological solitons that will be coming out in a paper by myself and Sam Whittington, hopefully within the next couple of months.
Okay. Okay, so RBS is asking, what are kind of the machine code instructions of the model right now? Well, so really the way we are writing our machine code is in terms of hypergraph rewritings. Is that the only way to do it? Probably not. There's probably a way to represent these sort of transformations between elements and relations. There's probably some grand category theory, some weird algebraic version of that. There's probably other ways. Anything that fundamental can be represented in many, many different ways. This is the way that seems to be the best match for us humans to understand what on earth is going on. But it's undoubtedly not the only way to do it. And maybe other kind of human traditions for mathematics and so on will allow us to get there. Jonathan's saying strong emergence has a specific technical definition. What is it?
Well, again, this is several questions behind, but yeah. So strong emergence is in complex systems theory is this very, very precisely defined thing, which is where you have an emergent system, but the macro structure has a top-down influence on the microstructure. So in other words, the behavior of the microstructure is different as a consequence of emergent properties of the overall system, which doesn't happen in all emergent systems, but it happens in some, and those are called the strongly emergent ones. So for us, something like quantum observation would be an example of a strongly emergent phenomenon, because that's something where there's an emergent feature of the multiway system, like an observer, but that observer, in attempting to construct a coherent thread of time, modifies details of the microstructure by, for instance, adding completion rules. So that would be an example of it where you have both a bottom-up and a top-down influence, and therefore you have what would be broadly characterized as a strongly emergent system.
See, here's a meta mistake of history of science for somebody like me. So, having kind of developed this whole complex systems idea in the early 1980s and sort of promoting this whole complex systems research, complexity theory thing, it finally takes off decades later, and there are zillions of people doing it. And I kind of naively assume just because I invented a bunch of the field means I actually understand what people talk about in that field now. That theory is wrong. Because so I've never heard of this concept, even though it's certainly something that so it's kind of interesting. At some point, when the child grows up, so to speak, and one no longer necessarily has one has it's that's one of the phenomena that happens. Okay, very interesting. It's always a shocking thing to me to look at science stuff that I developed years ago and then look at like textbooks people write about it and realize, oh my gosh, I don't really even understand anything that they're talking about in this textbook, even though they say I invented this thing. It's very it's a bizarre, and perhaps it's a good process, but it's a little bit of a strange one for me. Okay. RJ asks, are there arguments against the notion the universe is simulated as a result of discoveries in the project? Yes, I would say so. One of the features of this model is in this kind of rulal multiway graph, sort of all possible rules are being run. And so it doesn't leave a heck of a lot of room for the simulator to have anything to simulate about, so to speak. I mean, in other words, let me put off the answer to this question. I'm trying to write this thing about why does the universe exist. I think that really has to ask questions about kind of the way to think about the universe as a thing that is necessarily there and not something where one can talk about it is being simulated on some substrate and where there are choices about the simulation, because by the time all possible rules are being run, all possible formal rules are being run, and we're merely seeing a slice of those rules that we have chosen to sample, it no longer makes much sense to talk about kind of, could it be simulated, because it is all possible things. It is not something where you are making a choice. There was no outside the universe, sort of godlike figure that's making a choice. Let's pick this particular set of rules for this universe. It's everything formal is actualized, so to speak. So I think the answer is that the things we're understanding from this make it really not seem plausible that that's something that one can really think about. There's a question here from Bayes. What would dimension 0.001 behave like? Yeah, well, so you can make, I mean, in our, for example, a deviation of 0.001 deviation from 3 dimensions. What's that like? There is a subtle distinction between curvature and dimension. You ask, given that you start at a particular point in a space, how big is the sphere that you get to? How big is the ball you get to when you go a certain distance out, the so-called geodesic ball? What's the volume of that geodesic ball? Well, roughly it grows like r, the radius, to the power d, the dimension. But it has a correction that's associated with the curvature of that space. And distinguishing what's dimension and what's curvature, particularly for small dimension variations, it's not clear completely how you do that. And a bunch of people have done projects related to that. Jonathan's written a bunch about that. I think that one of the questions is, could you perhaps even formulate general relativity in terms of dimension change rather than curvature change? That seems to be a possibility, and at least for small gravitational fields and so on. And I think that's a kind of thing that, but we're still trying to understand what sort of phenomenologically is involved in a photon propagating through a 3.001 dimensional space. Roughly, I think you can use Huygens' principle of sort of every point on the wavefront of a propagating photon is a source of other spherical waves. And I'm kind of thinking we can use that to understand how things work in different dimensional space, and what the kind of effective refraction going into different areas of different dimensional space regions is, what the potential transition radiation doing that is, and so on, and hopefully figure out what that would actually look like in an astrophysical level. Jonathan had 3 question marks because he probably thought I was answering some question in a completely wrong way, but I don't know what the question is. So that was lost. Okay, we should probably wrap in a moment here, but a couple more here. Tarker is asking, was this model possible without computers? I think people like Hilbert and Einstein and so on 100 years ago were not conceptually that far away from some aspects of our model. Einstein, people have sent me many times a quote from Einstein in 1916, when just a year after he invented general relativity, saying, look, probably space is really discrete, but we don't have the tools right now to be able to analyze how that works. Hilbert spent basically 20 years between 1900 and 1920 trying to understand sort of the mathematization of going from an atomic description of things, of matter and so on, to a continuum description. He didn't really succeed in getting a good handle on that description. But the idea that space is discrete and sort of how that could work was something that was certainly in the air 100 years ago. People couldn't figure out how to make it work. The key thing that was missing was intuition about computational kinds of things, and phenomena like computational irreducibility, which in a sense, is quotes obvious from Gödel's theorem. But it's not actually obvious until you go and explore the computational universe and see a lot of empirical things happening, which is what I was able to do in the early 1980s. And I think so in a sense, if we were infinitely smart, we probably could see this without computers. But in actuality, you need to build these sort of towers of intuition and results and experiments that really only become possible with computers. I mean, I've often sort of said, I wonder whether the Babylonians actually did cellular automata. And if they'd known about, like, my Rule 30 cellular automata has a very simple rule and complicated behavior, if they'd known about that, would the history of science have been different? Well, I think the problem is that even if they had known about it, even if somebody had made a mosaic that looked like that, it would not have had a context in which to be understood. And I think a lot of what we're doing with computational irreducibility, with all these computational ideas, it has a context in which it can be understood. And that context is the very big development of kind of computation as a paradigm that's happened over the last 50 years or so. And that's, I think one needs that paradigm. And one also, as a practical matter in developing that paradigm, needs computers to do the experiments that let one understand that paradigm better. And I suppose the thing in my life that's been sort of a fortunate trajectory is that because I happen to do sort of physics and actual, quantum field theory and things like that when I was much younger, 40 years ago or so, more than 40 years ago now, and I also was deeply involved in sort of the development of this computational paradigm and in actually doing experiments in the computational universe. That combination of things is a sort of a strange coincidence of different things that sort of have led to various kinds of thinking about this kind of project. Not to mention some of Jonathan's wonderful convergences of working on both general relativity and theorem proving, which have both turned out to be relevant, although why those two things, it's like the mixing in individual people of very different kinds of ideas that have made possible this kind of thing. But I think, if computers had existed before Newton, for example, would we have had Newtonian mechanics? Would we have had something completely different? I'm not sure. I suspect it would have been rather different. I think that the emphasis, a lot of thinking about mathematics absent computers has in some cases been a bit distractive. For example, the non-primacy of time, the idea that time is just another dimension. That's something that mathematically seems pretty plausible, computationally seems very implausible. And so there are things like that that have been sort of slight, I would say, missteps as a result of going the sort of pure computation, pure mathematical route without computation. But so I think the answer is that in the end, some of the things we'll figure out. You could say, okay, you went on this long circuitous path that involved a lot of building up of intuition and so on. You could just go from the beginning to the end. You don't need all that stuff in the middle. That's just not the way the history of science and the history of ideas works. You need the stuff in the middle to contextualize things, to build up this kind of tower of intuition that's necessary to get to the next step. Okay, last thing here from Ike. Can our model explain cosmological inflation? I like the way that you put parenthetical cosmological there, because in the attempts to apply our formalism to economics, there's also the question of explaining the other kind of inflation in economics and the bizarre possibility that at some formal level they're related. But in cosmological inflation, the thing I was mentioning earlier, that our current thinking is that the universe kind of started infinite dimensional. And in starting infinite dimensional, you basically don't need the somewhat hack tower, which I was somewhat involved in building originally for sort of cosmological inflation. You don't really need that. And you don't need all these infinite number of parameters. You end up with something where the universe starts infinite dimensional and it cools down to being finite dimensional. That cooling process probably has certain universality. We were trying to work out a couple of weeks ago that the universality of that cooling process, haven't done it yet. It probably has some universal characteristics that we will be able to talk about. And certainly this sort of exponential closeness idea is immediately captured by starting in a higher dimensional space. And I kind of think that's the way this is going to work. And I think not only is it the way it's going to work, I think there are going to be some pretty robust predictions about kind of the structure of the very early universe and possibly some relics of that we might be able to see in the current universe. Jonathan, do you want to have a last comment on that?
No, I think that's pretty much right. I mean, so at a purely mathematical level, I mean, this is some analysis I did in the early relativity papers. We know that a universe that starts off effectively infinite dimensional and then undergoes a dimension phase transition can at least have the same conformal structure as one that underwent cosmic inflation. And the reason for that is effectively a way you can parameterize variable dimension is in terms of a variable speed of light, because when you have a hypergraph that exists in a higher number of dimensions, it has higher average edge connectivity. You can reach hypergraph vertices faster with smaller numbers of hyperedge traversals. So effectively, the whole spatial structure is more causally connected. And so it acts as though you're in a universe with a higher speed of light. And so one way you can formalize this idea of a phase transition from infinite to finite dimensions is as a phase transition from effectively infinite to finite speed of light. And then you can make connections to models that have already been studied in cosmology, like the things like the Pettit-Olbrecht model of variable speed of light cosmology. And you can show that this does indeed constitute a valid solution of at least the horizon and flatness problems of lambda CDM. And probably, although we don't know that this has not actually been calculated in detail yet, it's something I think we should try and do at some point, probably also constitutes a valid solution to the magnetic monopole problem as well. But that's much less understood, because that's not, unlike horizon and flatness, that's not a pure sort of geometrical structure of space-time problem. But certainly for the two big ones, horizon and flatness, for which you generally require cosmic inflation, that we know there is a way to solve using dimension phase transition.
Well, of course, the magnetic monopoles thing also brings in all kinds of other bizarre things, like the expansion of the universe in branchial space, and the question of whether there is a similar sort of cool down of Hilbert space, of some, dimensionality or something else of Hilbert space and branchial space. That will be a coming attraction of thinking about the way that the universe, what the universe does in terms of its, maybe the universe kind of cools down in physical space, but it still remains infinite dimensional in branchial space. Anyway, lots of coming attractions. All right, we should wrap up here, but appreciate people joining us, and I hope we're having a lot of fun with this project, in case you can't tell, and I hope people are having fun following what's going on with this project, and encourage people to get involved. Encourage people. I would say this project has room for many different kinds of skills, from sort of physics and mathematics skills to software engineering skills to we didn't even mention work Max is doing to make kind of GPU-enabled visualization technology and so on. There are many different ways to get involved, and I hope that is something that more people can get involved with. I think it's as I say, it's been a lot of fun. Looking forward to the next year and beyond with this project, and seeing how more and more features of our universe seem to be coming out of what we're doing. And I'm really curious how kind of at what point we get to check off all the sections of the physics textbook, so to speak, of yep, we got that, and at what point we get to be able to say, and now we can rewrite that section. My late friend Dick Feynman always used to be fond of saying, nobody understands quantum mechanics. And I was thinking, finally, we're going to be able to say, I think we actually understand quantum mechanics and a lot of other things. So it's an exciting thing. Well, thanks for joining us today. I should mention.
Summer school.
Yes, right. I should mention the summer school is coming up in June. It's a great place for people to get seriously involved with this project. Apply now. I'm not involved in the front lines of the application process. Sounds like Jonathan knows a lot more about it. It's relevant for people at a spectrum of stages of education. We actually have both our summer school and a high school summer camp. As Jonathan kind of alluded to, we had some wonderful high school students this last year who've actually worked on really interesting things with the physics project. I'm sure they will have terrific careers. I think that they're starting young, as I did and as Jonathan did with science. But so there's both down at the sort of high school level, there's some opportunity but there's also the kind of the main part of our summer school is undergraduates, graduate students, postdocs, and beyond, and people who have learnt the same things, not in those kinds of settings. Please apply and potentially join us there. We also have study sessions that are kind of on-ramps to things like the summer school and so on. And we have a number of research affiliates now who joined us through our study session programs. Another thing I should mention now that is we also have a new thing this year, responding to the pandemic times and so on, which is we have a sort of full gap year program both for people between high school and college and between college and graduate school. And that's a kind of a full year program where we expect at the summer school and so on, the kind of concept is for people to do an original research project. The gap year program will be an extension of that involves a much more in-depth, perhaps even more than one project getting done. And we have kind of a nice piece of that, which is the summer school will be virtual again this year. The gap year program has a sort of optional physical component that can happen at a variety of locations around the world that happen to be correlated with the places where our company has offices and so on. That's another opportunity which we are taking applications for our gap year program that will start up, I guess, this late this summer, and that's another thing. But anyway, and we also should mention, okay, we're just going to promote our own things here. I mentioned membership program for Physics Project, swag and more. And I also should mention other live streams we're doing. I personally have been doing a couple of series of live streams, 3 series of live streams, one on Fridays, Science and Technology Q&A for kids and others, where I try and answer questions about science and technology. I hope they've been educational to people who've listened to them. They've been very educational for me. I have definitely become a better explainer of things as a result of that process. So, and I like very much the kinds of questions we get there, and I encourage people to join. I've also been doing on alternating Wednesdays. I've been doing a history of science and technology Q&A and a business and innovation Q&A. And that's probably about it for now. Well, thanks very much for joining us here, and look forward to more live streams, more physics, more ideas, more results in the future.